Perhaps you've had a long day, one filled with noise and haste, and now you're seeking a quiet place to rest your mind. Or maybe you're simply someone who likes to fall asleep thinking about the stars, contemplating the grand, silent story of the cosmos. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Whatever has brought you here, know that this is a place for rest. There's nothing to do, nothing to solve. There is only a story to listen to, a gentle journey we can take together. Tonight, we're going to travel forward. Far, far forward in time. We'll travel past the lives of stars and the dance of galaxies, to a time when the universe prepares to take its last, gentle breath. This isn't a story of endings in the way we often think of them, full of sound and fury. Instead, it's a story of a deep and final quiet, of a stillness that will eventually claim everything. So find a comfortable position. Let your body feel heavy and supported. Feel the gentle rise and fall of your own breath, in and out. Each breath is a small anchor to this moment. And as you breathe, we'll begin our journey into the deep future. There is nothing to fear. There is only wonder to gently explore as you drift towards sleep. The story we thought we knew, the great exhale. For a very long time, our understanding of the cosmos has been pointing towards one particular kind of ending. It's a story written in the language of physics, in the laws that govern energy and time. A story of a great, cosmic exhale, an expansion that never ceases, a cooling that never ends. We called it the heat death of the universe. And for a long while, we believed this was the definitive, final chapter. To understand this story, we must first look around us, at the universe as it is now. We live in a glorious age, an epoch of brilliance that scientists call the Stelliferous Era. Put simply, it's the era of the stars. Look up into the night sky in your mind's eye. See the sprinkle of diamonds against black velvet. Each point of light is a sun, a colossal furnace burning across unimaginable distances. These stars are gathered into great, swirling cities of light we call galaxies. Our own Milky Way is just one of hundreds of billions, perhaps trillions, of such galaxies. It's an age of activity, of creation, of light, and of warmth. The universe is alive with the hum of fusion in stellar cores, the graceful spin of spiral arms, the collision and merging of galaxies in a dance that takes billions of years. This is our home. This is the universe in its vibrant, brilliant youth. But even here, in this age of light, a fundamental rule of the cosmos is quietly at work. It's a principle known as entropy. You don't need to understand all the math. Just think of it this way. Entropy is the universe's tendency toward disorder, toward an evening out of things. Imagine a single drop of dark ink in a glass of clear water. At first, it's a concentrated, ordered thing. But slowly, inevitably, it spreads out. The tendrils of ink unfurl, becoming fainter and fainter, until the entire glass of water is a uniform, pale gray. You can't undo it. You can't gather the ink back into a single drop. The change is irreversible. That spreading, that mixing, that gentle slide from order to disorder, that is entropy. This law, the second law of thermodynamics, is perhaps the most steadfast law in all of physics. It states that in an isolated system, like our universe as a whole, entropy can only increase. Energy naturally flows from places of high concentration to places of low concentration. Heat flows from a hot star out into the coldness of space. It doesn't flow back. This one-way street for energy is the engine of change in our universe. It is also the arrow of time, forever pointing from the ordered past of the Big Bang to a more disordered future. And as we peer into the far, far future of that first story, the story of heat death, we see this gentle, relentless increase of entropy guiding everything toward a final, uniform state. The great exhale of the cosmos, carrying all heat and energy and light further and further apart, until everything is spread as thin as that ink in the water. The fading of the light, the degenerate era. Our journey now takes us past our own time, beyond the lifespan of our sun and even our Earth. We travel forward hundreds of billions, then trillions of years. The Stelliferous Era, the age of stars, can't last forever. Like a cosmic fireplace, the universe has a finite amount of fuel. The vast clouds of gas that form new stars aren't infinite. And one by one, across the cosmos, the stellar nurseries grow quiet. The formation of new stars becomes rarer and rarer, until eventually, the last star flickers into existence and begins its long life. And as the creation of new stars ceases, the old ones begin to die. The most massive stars, the brilliant blue giants, are the first to go. They live fast and die young, ending their lives in spectacular supernova explosions that briefly outshine entire galaxies. They leave behind the most exotic objects in the cosmos, either incredibly dense neutron stars or the ultimate enigmas, black holes. Smaller stars, like our own sun, have a more gentle end. When their fuel runs low, they'll swell into red giants, their outer layers puffing away into space as beautiful, glowing planetary nebulae. Left behind at the center will be the star's core, a hot, dense, Earth-sized ember called a white dwarf. Imagine, for a moment, the universe trillions of years from now. The great age of starbirth is over. The galaxies are no longer bright, swirling pinwheels of light. They are becoming ghostly collections of stellar remnants. The only light comes from the last, long-lived red dwarf stars, the universe's most frugal hearths, which sip their fuel so slowly they can shine for trillions of years. But even their light is a dim, crimson glow. The universe is becoming a much darker, much colder place. This is the beginning of what scientists call the Degenerate Era. The name might sound grim, but it simply refers to the degenerate matter that makes up the white dwarfs and neutron stars that now populate the cosmos. Let's follow one of these white dwarfs, a final ember from a sun much like our own. For trillions upon trillions of years, it will radiate its remaining heat into the void. Its brilliant white light will slowly fade to yellow. Over more time than our minds can truly hold, it will shift to a soft orange, then a dull cherry red. The cooling process is incredibly slow, a thermal sigh lasting for an eternity. After quadrillions of years, its light will be gone from the visible spectrum, a dead star drifting through the eternal night. It has become a black dwarf, a cold, crystallized diamond the size of a planet, forever silent. Entropy is at work here, in its slow, patient way. The concentrated heat of that white dwarf has been spread out, dispersed into the vast, cold emptiness. The star's order has been given over to the growing disorder of the cosmos. The ink is spreading ever thinner. The galaxies themselves are also changing. Driven by the relentless expansion of space, they are moving further and further apart. Any galaxies not gravitationally bound will eventually recede from one another so far and so fast that light from one will never again reach the other. They will cross a cosmic horizon, disappearing from each other's view forever. The universe becomes a collection of isolated island galaxies, each one a darkening graveyard of stellar corpses. The universe is quieter now. The hum of stellar fusion has all but ceased. The sky, seen from a planet orbiting one of the last dying stars, would be almost completely black. The age of light is over. The slow fade is nearly complete. The reign of shadows, the black hole era. Our journey continues, onward into a future so deep it defies all human scales of time. We are now perhaps a duodecillion years from the Big Bang. That's a 1 with 39 zeros after it. The last black dwarf has cooled to near absolute zero. The last neutron star has settled into its final, cold state. The universe is now a vast, dark, and almost empty place. The expansion has carried the island galaxies so far apart that the distances are functionally infinite. The universe is a void, populated only by cooled, dead stars, planets, and dust, all slowly losing orbital energy and spiraling toward the center of their ghostly galaxies. And at the center of each of these galaxies lies a monster, a supermassive black hole. In this profound future, these black holes are the only active things left. They are the heirs of the cosmos. This period is known as the Black Hole Era. For an almost unimaginable length of time, these silent giants will be the main characters in the cosmic story. They'll slowly sweep up the stray matter of their dead galaxies. A wandering black dwarf, after a journey of quintillions of years, might finally fall into the central black hole, a final, silent gulp in the darkness. It would seem that these objects, whose gravity is so strong that not even light can escape, would be the final state. That matter and energy, once fallen in, are lost forever. It would seem this is the ultimate prison. But even here, facing the ultimate abyss, there is a process. A final, slow release. A concept first imagined by the physicist Stephen Hawking. It's called Hawking radiation. Imagine the vacuum of space not as empty, but as a simmering soup of virtual particles, pairs of particles and antiparticles that pop into existence for a fleeting moment before annihilating each other. It happens everywhere, all the time. Now, imagine this happening right at the edge of a black hole's event horizon. Just as a pair of particles pops into being, one might fall in while the other escapes. From the outside, it would look as though the black hole just emitted a particle. Because of the strange rules of energy, the particle that fell in has a kind of negative energy, which reduces the mass of the black hole by a tiny, tiny amount. The particle that escaped carries away that mass as energy. This process is impossibly slow. For a black hole the mass of our Sun, it would take around 10 to the power of 67 years to evaporate completely. For the supermassive black holes at the centers of galaxies, it could take a Google. That's a 1 with 100 zeros after it, of years to disappear. This is the final breath of the massive objects in the universe. Not a roar, but a whisper. A slow, quantum hiss, bleeding energy back into the void over timescales that make the current age of the universe seem like less than a single heartbeat. Imagine this universe, a space so vast and empty that distance loses its meaning. And scattered throughout this infinite blackness are these colossal black holes, each one slowly, silently, evaporating. Releasing a slow trickle of low-energy particles back into the cosmos. Entropy is still at work. The highly ordered mass trapped inside the black hole is being converted into disordered, low-energy radiation, spreading out evenly across the void. The final concentrations of energy are being smoothed away. The ink is becoming impossibly, perfectly diffuse. The final stillness, the dark era and heat death. We travel now to the end of that first story. To the conclusion of the great cosmic exhale. We are a Google of years in the future, perhaps more. The last supermassive black hole has finally evaporated. Its final particle has radiated away into the void. The hiss has faded to silence. This is the beginning of the dark era. And it's an era that will never end. What is the universe now? It's a sea of fundamental particles. A vast, ever-expanding soup of photons, neutrinos, and electrons, all flying aimlessly through the near-total emptiness. The density is so low that a particle might travel for 1 trillion years without ever encountering another. The temperature of the universe is now just a tiny fraction of a degree above absolute zero. And it will continue to fall, forever approaching, but never quite reaching, that final state of zero motion. This is heat death. It is a state of maximum entropy. The ink is now perfectly mixed with the water. The water is a uniform, unchanging gray. There are no hot spots and no cold spots. There's no flow of energy because energy is perfectly distributed everywhere. And without a flow of energy, nothing can happen. No work can be done. No information can be processed. No change can occur. The concepts of time and causality begin to lose their meaning. If one moment is indistinguishable from the next, does time still pass? The universe has taken its final breath. And now, it is still. It isn't a violent end. It isn't a fiery end. It's an end of perfect peace. Of absolute quiet. Imagine a lake on a windless night, after the very last ripple has subsided. The surface is a perfect, unbroken mirror. That is the universe in the state of heat death. All the complexity, all the structure, all the fire and light and life that once existed has been smoothed away into a final, simple equilibrium. The grand cosmic story, with its chapters of fusion and gravity, of life and thought, has been told. The book is closed, and all that remains is a silent, endless epilogue of cold peace. For a very long time, this was the end of the story we were telling ourselves. A story of a final, gentle fade to black. A new whisper from the cosmos, the great inhale. But as we listened to the silence at the end of that long story, it turns out that science has been listening, too. Listening to the light from the most distant galaxies, measuring the expansion of space with ever greater precision. And very recently, it has heard a new whisper. A different possibility. A new chapter that might change the ending entirely. For decades, we thought the expansion of the universe was accelerating, driven by a mysterious force we call dark energy. This acceleration was the very thing pointing to the cold, empty future of heat death. But the newest data, from projects that map the cosmos in incredible detail, has begun to suggest something different. Some physicists now look at this data and see a hint that dark energy might not be constant. That its effect might be weakening. What does this mean, in the simple language of our sleepy story? It means the push might not be forever. It means the great cosmic exhale might not be the final act. If this new evidence holds, it suggests that the force of dark energy, which has pushed everything apart for billions of years, will eventually fade. And as it fades, a more familiar force will once again become the master of the cosmos: gravity. This new story suggests that in the far future, perhaps around 11 billion years from now, the expansion of the universe could slow to a halt. The galaxies, which have been rushing away from each other for so long, might pause at the peak of their journey. And then, slowly, gently, they could begin to fall back. This isn't the story of a final breath exhaled into the void. This is the story of a great, cosmic inhale. The journey homeward. Let's leave the cold, quiet future of heat death and step into this other dream, this other possible future. A future where the universe decides to come back together. We are, say, 20 billion years from now. The expansion has stopped, and the universe is now contracting in what's known as the Big Crunch. This isn't a violent, sudden event. It's as slow and graceful as the expansion that came before it. From a vantage point on a world in this future, you'd notice the change in the sky. For billions of years, the light from distant galaxies was redshifted, stretched to redder wavelengths as they sped away. But now, the light would begin to be blue-shifted. The galaxies are on their way home. The universe is beginning a slow, cosmic gathering. The vast voids of space, which had been growing for eons, would now begin to shrink. The island galaxies, once lost to each other over the cosmic horizon, would drift back into view. The night sky would become more and more crowded with the light of returning galaxies. In this scenario, the long, dark eras of stellar death and black hole evaporation would never happen. The universe wouldn't have time to fade into a cold graveyard. Its end would have a very different character. As the universe contracts, everything gets closer. The density of matter increases. But more importantly, the density of energy increases. The background radiation of the cosmos, the faint afterglow of the Big Bang, would now be compressed. And as it's compressed, it would get hotter. The sky would begin to glow. First, it would be a faint microwave hum, then it would warm into the infrared. Eventually, the entire sky would shine with a dull, red light. The darkness of interstellar space would be banished. The universe would be filling with warmth and light again, not the light of new stars, but the light of the universe itself, the energy of all of space warming up as it contracts. As the great inhale continues, the background temperature would rise past the boiling point of water. Planets would be sterilized. The stars themselves would begin to feel the heat. The universe would become a cosmic furnace. The stellar remnants, white dwarfs and neutron stars, would be cooked by the rising ambient temperature. In the final moments, the temperature would become so high that stars, planets, and even black holes would dissolve into their constituent particles. The universe would be returning to a state much like the one it was born from, a hot, dense plasma. This is the big crunch. But we can think of it not as a crunch, but as a return. A closing of the circle. All the matter and energy that exploded outward in the Big Bang, that spread out to form galaxies and stars and is now coming back to a single point. A cosmic reunion. The story ends not in a cold, eternal stillness, but in a hot, dense singularity. A return to the beginning. Two dreams of the end. And so, we are left with two profound, and profoundly different, dreams of the end. One dream is of a great exhale. A universe that expands forever, its light and heat spreading ever thinner until all is a cold, silent, and eternal peace. The heat death. A final, still breath. The other dream is of a great inhale. A universe that expands, but then returns. A slow gathering of everything, a journey home to a hot, dense state, closing the cosmic loop. The big crunch. A breath drawn back in. Which of these stories is the true one? As of right now, as you lie here listening, we aren't entirely sure. The whispers from the cosmos are new, and science is still trying to interpret them. The universe has not yet revealed its final chapter to us. And perhaps there's a gentle comfort in that. The beauty isn't just in knowing the answer, but in the wonder of the question itself. Both stories are told in the language of mathematics and light. Both are born from our deep and abiding need to understand our place in the cosmos. Whether the universe fades into a perfect stillness or gathers itself for a great return, the journey is one of sublime and patient grandeur. It's a story written on a canvas so large, and with a timeline so long, that our own lives are but a flicker of a firefly in a summer twilight. But our flicker is a part of it. The consciousness that allows you to lie here and ponder these things is a product of that same universe. You are the cosmos, dreaming of itself. If these gentle journeys through the cosmos help you find your rest, I would be so grateful if you would subscribe and join me again. And if you feel so inclined, you can share a thought in the comments. Which cosmic dream do you find more peaceful? The silent, cold stillness, or the warm, cosmic return? There's no right answer, only your own feeling of wonder. But now, it's time to leave these futures, trillions of years from now. Let's draw our awareness back. Back from the end of time, back to the here and now. Bring your attention away from the fading stars and contracting galaxies, and just feel the gentle weight of your own body. Feel the support of the bed beneath you. Notice the soft fabric against your skin. Listen not for the hiss of an evaporating black hole, but for the quiet sounds of your room. And most importantly, bring your awareness to your own breath. That gentle, rhythmic cycle. An inhale and an exhale. Each breath you take is a small, personal echo of the great cosmic cycles we've just explored. A quiet expansion and a gentle return. There's no need to think about entropy or the fate of the cosmos any longer. The journey is done. You are here, now, safe and at peace. All that's left to do is let the tide of your own breathing carry you out onto the quiet sea of sleep. The universe will continue its story, but yours, for tonight, is to rest. And now, it is time to rest. Sweet cosmic dreams. Why everyone is wrong about the expanding universe. Most of us have an image of the expanding universe. It is one of galaxies moving through a vast emptiness, like fragments from a distant, ancient explosion. It is an intuitive picture. It feels right. But that picture is fundamentally wrong. The galaxies are barely moving at all, and the true story is quieter and far stranger. Space itself is stretching. This single understanding rewrites the story of our cosmic beginning and its ultimate end. What we think we know about the universe is only the first part of a much deeper story. And this is a journey to understand the rest of it. When we hear the words Big Bang, our minds often form a very specific image. A single point in a pre-existing darkness. Then, a detonation, flinging all matter outwards. In this picture, galaxies are like embers coasting away from a central fire. Our Milky Way is one piece, Andromeda is another, all of them flying through a static, unchanging void. This is the explosion model. It is simple, dramatic, and for a long time, it has been the default mental picture for many. It makes a certain kind of sense. Explosions send pieces flying outwards from a center. And since we see galaxies moving away from us, it seems logical to conclude we are witnessing the coasting debris from a singular event. This picture implies a few things. It suggests a center to the universe, the point where the explosion happened. It suggests there might be an edge, where the fragments have not yet reached. And it implies that galaxies are objects moving through space. For a long time, this was a reasonable guess, a natural extension of our everyday experience. But the universe does not operate by everyday rules. The cosmos is not a bomb scene, and its expansion is not a story of motion, but of creation. The common picture is profoundly and beautifully wrong. The journey to understanding why begins not with a bang, but with a quiet revelation. Our story starts about a century ago. In the early 1920s, the consensus was that the entire universe consisted of one single galaxy, our own. The fuzzy patches of light in the sky, then called spiral nebulae, were thought to be swirling clouds of gas inside the Milky Way, perhaps new solar systems in the process of forming. Then came Edwin Hubble. Stationed at the Mount Wilson Observatory in California, he had access to the most powerful telescope in the world. And he pointed it at one of the brightest spiral nebulae, a patch of light in the constellation Andromeda. Night after night, Hubble captured photographic plates. In 1923, he saw something incredible. A star within the nebula that was blinking, varying in brightness over a regular cycle. He recognized it as a Cepheid variable. Work by another astronomer, Henrietta Swan-Leavitt, had shown a direct relationship between how fast these stars pulsate and their true brightness. This was the key. By measuring how fast the star blinked, Hubble could calculate how bright it really was. By comparing that to how dim it appeared, he could calculate its distance. When he did the math, the result was staggering. The star, and by extension the Andromeda Nebula itself, was almost 1 million light-years away, far beyond the boundaries of our own Milky Way. Later measurements would refine this distance to over 2 million light-years, but even his initial calculation was world-shattering. Andromeda was not a cloud in our backyard. It was an entire, separate galaxy, an island universe, like our own. In a single stroke, Hubble had doubled the known universe. But this was only the prelude to a revelation that would not just expand the size of the cosmos, but set it in motion. Hubble, along with his assistant Milton Humason, began a grand survey. They measured distances to these new galaxies, but they also looked at another piece of information, one that came from the light of the galaxies themselves. When light is passed through a prism, it splits into a spectrum, a rainbow of colors interrupted by dark lines. These lines are the chemical fingerprints of the galaxy that emitted the light. An astronomer named Vestos Slipher had noticed something strange about these lines. For nearly all galaxies, the pattern was shifted toward the red end of the spectrum. This is known as redshift. It has a familiar cousin in the world of sound, the Doppler effect. As an ambulance moves away from you, the sound waves stretch, making the pitch lower. Light behaves in a similar way. If an object is moving away from us, its light waves get stretched, shifting its spectrum towards red. Stelliferous had found that almost every galaxy he looked at was redshifted, meaning almost every galaxy was moving away from us. It was a strange observation. Why would everything be fleeing from our location? He had the what, but not the how far. This is where Hubble's work became essential. He had the missing piece: distance. Beginning in 1929, he started to plot his data. On one axis, he put the distance to a galaxy. On the other, he put its redshift, how fast it was moving away. A clear pattern emerged. The farther away a galaxy was, the faster it was receding from us. A galaxy twice as far away was moving twice as fast. This direct relationship became known as Hubble's law. The implication was inescapable. The universe was not static. It was growing. The universe itself was expanding. The evidence was clear, yet this is where the great misconception takes root. If everything is moving away from us, it still feels like we are at the center of an explosion. But the truth revealed by Hubble's law is infinitely stranger. The secret is in what, exactly, is doing the expanding. So, we have the observation: distant galaxies are moving away, and the farther they are, the faster they recede. The explosion model seems to fit, but it creates a paradox. It would mean we are at the exact center of the universe. This would make our position uncomfortably special, violating a core idea in cosmology known as the Copernican principle, which states that we are not privileged observers. So how can everything be moving away from us, without us being at the center? This is the point where we must leave our intuition behind. The galaxies are not flying through space. Space itself is expanding. It is not that galaxies are moving like ships away from a static shore. It is that the ocean itself, the fabric of space-time, is stretching, carrying the galaxies with it. The galaxies are mostly stationary in their local patch of space. This single idea resolves the paradox. Because if space itself is stretching everywhere, then an observer in any galaxy would see the exact same thing. There is no center to the expansion. Or, to put it another way, every point can be considered the center. This is a fundamental distinction. The idea that empty space is not a passive backdrop but an active, dynamic entity is the single most important concept in modern cosmology. To grasp it, we need simpler models. Our brains did not evolve to picture the stretching of spacetime. So we turn to two classic analogies. The first is a loaf of raisin bread dough. Imagine a lump of unbaked dough with raisins scattered throughout. The dough is space, and the raisins are galaxies. As the loaf bakes, the dough expands. Notice what happens. The raisins are not moving through the dough. They are being carried along as the dough itself expands. From the perspective of any single raisin, all other raisins are moving away. A raisin that was 1 inch away is now 2 inches away. One that was 2 inches away is now 4. This perfectly replicates Hubble's law. And it is true no matter which raisin you choose. There is no center. The expansion is happening in the dough itself. The second analogy is an expanding balloon. Imagine dots drawn on the surface of a balloon. The two-dimensional surface represents our three-dimensional universe. The dots are the galaxies. Now, inflate the balloon. As the rubber stretches, all the dots move farther apart. Again, the dots are not skittering across the surface. The surface itself is expanding, carrying them with it. This analogy helps with another difficult question. What is the universe expanding into? The universe is, by definition, everything. There is no outside. On the balloon, the expansion happens within the surface itself. In the same way, the 3D space of our universe is stretching without needing a fourth dimension to expand into. The universe is expanding into itself. These analogies are not perfect. A loaf has a crust. A balloon is embedded in a room. The universe, as far as we know, has no edge and is not embedded in anything. But they help us make the critical mental leap. The action is happening to space itself. Once we accept that space is stretching, a series of consequences follows. First, the cosmic speed limit. We are taught that nothing can travel faster than the speed of light. Yet, Hubble's law seems to challenge this. The expansion rate, the Hubble constant, is not a single agreed-upon number. Measurements of the early universe suggest a value of around 67 km per second per megaparsec, while measurements of the local universe suggest a slightly faster rate of around 73. This disagreement is known as the Hubble tension, an active area of research. But using either number, if you do the math, you find that at a distance of about 14 billion light-years, the cumulative expansion of space means a galaxy is receding from us faster than the speed of light. Does this break Einstein's law? No. The reason is the crucial distinction we have been making. The speed limit applies to objects moving through space. These distant galaxies are not traveling through space at that speed. They are being carried by the expansion of space. Because it is spacetime itself that is stretching, the cosmic speed limit is not violated. It is a loophole in physics, and it means that a vast number of galaxies in our observable universe are already receding from us faster than light. Their light forever unable to reach us if emitted today. This leads to another question. If space is expanding, is the Earth expanding? The answer is no. On local scales, other forces are much stronger. The forces holding your atoms together are trillions of times stronger than the pull of cosmic expansion. Gravity is also stronger. The Sun's gravity keeps the Earth in its orbit. Even our galaxy is held together by its own gravity. In fact, our nearest large neighbor, Andromeda, is moving toward us, and is expected to merge with the Milky Way in about 4.5 billion years. Its local motion, driven by gravity, has overpowered the expansion between us. It is the vast, empty spaces between galaxy clusters that are truly stretching. Like the raisins in the bread, the galaxies themselves stay the same size, while the dough between them grows. This understanding of space also rewrites the story of our beginning. The old model of the Big Bang was an explosion in space. The new model tells us the Big Bang was an explosion of space. If the universe is expanding today, then in the past, it must have been smaller. If you run the clock backward, the universe contracts. It gets denser and hotter. Rewind it all the way back, about 13.8 billion years, and everything in our observable universe, all matter, energy, and space itself, was compressed into an unimaginably hot and dense state. The Big Bang, therefore, was not an event that happened at one location in a pre-existing void. There was no empty space for it to explode into. Space and time, as we know them, began at that moment. The Big Bang happened everywhere, because that single point was everywhere. It was the birth of spacetime itself, which has been expanding and cooling ever since. This model makes a testable prediction. If the early universe was incredibly hot and dense, it should have been filled with an intense, uniform glow. As the universe expanded, that light should have stretched with it, red shifting down to the microwave part of the spectrum. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, accidentally discovered this very glow. A faint microwave hiss, coming from every direction. They had found the afterglow of creation, the cosmic microwave background. It was quiet confirmation of an expanding universe. But a final, shocking plot twist was yet to be discovered. For most of the 20th century, the expansion was seen as a battle. The outward push of the Big Bang on one side, and the pull of gravity on the other. The fate of the universe depended on which force was stronger. In the 1990s, two teams of astronomers set out to measure the rate at which the expansion was slowing down. To do this, they used a specific type of stellar explosion called a Type Ia supernova. These explosions always happen with a predictable brightness, making them excellent, standard candles, to measure vast cosmic distances. The plan was to find these distant supernovae, measure their distance by their faintness, and measure their redshift to see their speed. This would chart the history of cosmic expansion. As the data came in, both teams found something baffling. The most distant supernovae were consistently fainter than they should have been. This meant they were farther away than expected. And if they were farther away, it meant that the expansion of the universe had not been slowing down. For the past 5 billion years, it has been accelerating. This discovery, which earned the 2011 Nobel Prize in Physics, turned cosmology on its head. Some other, mysterious influence was at play, pushing the universe apart at an ever-increasing rate. Scientists have given a name to this mystery: dark energy. It appears to be a property of space itself, an energy in the vacuum that exerts a negative, repulsive pressure. Based on our best measurements, it accounts for nearly 70% of the universe. We do not know what it is, but its discovery has dramatically altered our vision of the cosmos's ultimate destiny. The discovery of acceleration rewrote the final chapter. The old idea of a big crunch, where gravity pulls everything back together, seemed unlikely. Instead, we appeared to be headed for a far colder, lonelier finale, known as the Big Freeze. Driven by dark energy, the accelerating expansion would push galaxies not bound to us ever faster, until one by one, they crossed a cosmic horizon. Their light redshifted into oblivion, their presence erased from our sky. The night sky of the distant future would be dark, populated only by the dying stars of our own merged, Milkomeda, supergalaxy. Over trillions of years, even these stars would burn out. Over unimaginable timescales, matter itself might decay. And finally, even supermassive black holes would evaporate. What would be left is a universe that is vast, cold, dark, and empty. A silent, eternal emptiness. For a long time, this was the accepted final chapter. But the story of the cosmos is one of constant revision, where new observations challenge old ideas. Very recent data has begun to introduce a new possibility, one that complicates the idea of eternal acceleration. Some interpretations suggest that dark energy might not be constant, and that in the distant future, the expansion could slow, stop, and reverse, leading after all to a big crunch. This question is not settled. It reminds us that our understanding is always incomplete, and that the ultimate fate of the universe is still a story being written. This journey, from a simple picture of an explosion to a universe born from stretching space, with a future still being debated, shows how science works. It is a process of careful observation, a willingness to abandon comfortable ideas, and a slow convergence on a better explanation. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. The journey is always just beginning. So, the picture of galaxies flying through space like shrapnel is wrong. It is a natural starting point, but it fails to capture the profound truth of our reality. The real story, supported by a century of evidence, is that space itself is a dynamic entity. It stretched into existence some 13.8 billion years ago. It carries galaxies with it. It can expand faster than the speed of light without breaking any laws. And its expansion, driven by a mysterious dark energy, is dictating a cosmic story whose final chapter has not yet been read. To understand the expanding universe is to undergo a fundamental shift in perspective. To realize we live not on a static stage, but within the very fabric of the performance itself. The stage is growing, and the actors are being pulled apart. The next time you look up at the night sky, remember that you are not just looking out into space. You are looking at the story of space itself. And we are here, for a brief cosmic moment, to witness it. The cosmic war that will decide our final fate. For most of human history, the story of the universe felt knowable. It was a quiet, predictable story. A universe born in fire and destined, one day, to grow old and fade peacefully into the dark. We imagined it was all governed by one familiar force, gravity. The same gravity that holds our feet to the earth and keeps our world in orbit was surely the master of our collective fate. The expansion of the universe, started by the Big Bang, seemed to be gradually slowing down. The immense pull of countless galaxies and stars was acting as a gentle brake on reality. The only real question was how it would end. Would gravity eventually win, pulling everything back together in a big crunch? Or would the expansion just coast to a quiet standstill, leaving a universe that was static and eternal? It was a comfortable thought. A story with a beginning, a middle, and an end we could almost foresee. But what if that story is wrong? What if the end is not a quiet slumber, but the outcome of a silent, cosmic tension that has already been underway for billions of years? What if the peace we thought we understood was just the quiet before a profound change? A hidden influence is competing for control of our universe, an invisible current pulling at the fabric of spacetime itself. And as our understanding deepens, it seems the final chapter of reality will be nothing like we imagined. The story of our universe and its ultimate fate has been reopened. The quiet contest for the cosmos is happening now, and we are living in the time that may very well decide the outcome. The day our story changed, a discovery of cosmic proportions. The story of this cosmic tension begins not with a dramatic flourish, but with a flicker. A series of faint, impossibly distant dying stars that would quietly rewrite our understanding of the cosmos. For decades, astronomers had been refining the legacy that began with Edwin Hubble in the 1920s. Through patient observation, Hubble revealed that the universe was not static. Galaxies, great islands of stars like our own, were all moving away from us. And the farther away a galaxy was, the faster it was receding. This was the first hint of the Big Bang, the idea that the universe began in an incredibly hot, dense state and has been expanding and cooling ever since. To picture this, you might imagine a loaf of raisin bread dough rising. As the dough expands, every raisin moves away from every other raisin. From the perspective of any one raisin, all the others appeared to be rushing away, and the ones farthest away moved the fastest. This is what Hubble saw. Our place in the universe isn't special. This expansion is happening everywhere. The logical next step was to measure the asterisk change in that expansion. The universe is filled with matter, stars, gas, and the invisible substance we call dark matter. All of this has gravity, and gravity pulls things together. Therefore, the combined gravity of everything should be acting like a brake, slowing the expansion down over billions of years. The great quest of late 20th century cosmology was to measure this deceleration. The answer would tell us our ultimate fate. A strong deceleration meant a future collapse, the Big Crunch. A weaker one meant the universe would expand forever into a cold, dark future. To measure this, astronomers needed something called a standard candle. Imagine you're in a dark field, and you see a single candle flame. Is it a bright candle far away, or a dim candle nearby? It's hard to be sure. But if you knew that all candles of a specific type had the asterisk exact same intrinsic brightness, you could judge their distance with precision. If it appears dim, it must be far away. If it appears bright, it must be close. In cosmology, the best standard candles we have are type Ia supernovae. These are stellar explosions that happen when a dense, dead star called a white dwarf pulls too much material from a companion. This process is remarkably consistent, and the supernovae all reach a peak brightness that is incredibly uniform, allowing astronomers to use them as cosmic mile markers. In the late 1990s, two independent teams of astronomers set out to find and measure dozens of these distant supernovae. One team was led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees. Their goal was to look so far back in time that they could detect the universe's expected slowdown. They would measure the distance to these supernovae using their brightness and compare it to their redshift, which shows how fast they are moving away. As the data came in, something felt wrong. The most distant supernovae, the ones that should have appeared brighter because the expansion was supposedly slower in the past, were consistently dimmer than they should have been. They were fainter, which meant they were farther away than the models predicted. The teams checked and rechecked their work, looking for some subtle error. But the conclusion was hard to escape. The only way for these supernovae to be so far away was if the expansion of the universe wasn't slowing down at all. In the time since those stars exploded, the expansion had actually sped up. It was a discovery that quietly unsettled the foundations of cosmology. It was like throwing a ball into the air and watching it, instead of slowing down, suddenly accelerate away into the sky. It did not seem to make sense. Gravity pulls, it doesn't push. Something else had to be at work, something overpowering gravity on the largest scales. In 1998, the world was told the news: the expansion of the universe is accelerating. For this work, Perlmutter, Schmidt, and Rees would later receive the 2011 Nobel Prize in Physics. But they had also revealed a ghost in the machine of cosmology. They had found evidence for a new, mysterious component of our reality, an influence whose existence almost no one had predicted. They called it dark energy. The silent cosmic war had been happening all along, and humanity had just realized it was taking place. The reigning story: Lambda CDM and a cold, lonely end. The discovery of cosmic acceleration sent a quiet shockwave through science. The neat picture of a universe governed only by gravity was gone. A new, dominant influence had been revealed, and it was winning. This influence, dark energy, seems to make up about 68% of everything in the universe. The ordinary matter that makes up you, me, the planets, and the stars? That's less than 5%. The other 27% is dark matter, the strange substance whose gravity holds galaxies together. This means over 2/3 of our reality is made of something we cannot see, cannot touch, and are only just beginning to understand. So, what is dark energy? The honest answer is, we don't know for sure. But the leading idea takes us back to Albert Einstein. When he developed his theory of general relativity, the common belief was that the universe was static. His own equations, however, showed that a universe full of matter should collapse under its own gravity. To fix this, Einstein added a mathematical term to his equations, which he called the cosmological constant, represented by the Greek letter lambda, lambda. It represented an intrinsic energy of empty space, a kind of outward push woven into spacetime itself, which would perfectly balance gravity. When Hubble later discovered the universe was expanding, Einstein reportedly called the constant his biggest blunder. But in a beautiful twist of scientific history, the discovery of cosmic acceleration brought it back. Scientists realized this cosmological constant, this energy of the vacuum, could be the very dark energy they were looking for. Think of it this way: as the universe expands, matter gets diluted. The density of galaxies and gas decreases as the volume of space grows. But if dark energy is an energy of space itself asterisk, then as more space is created, its density remains constant. Early in the universe, when things were much denser, the gravity of matter was the dominant force, and the expansion was slowing down. But as the universe expanded, matter thinned out, and its gravitational grip weakened. About 5 billion years ago, a tipping point was reached. The repulsive push of dark energy finally overtook the attractive pull of gravity, and the era of acceleration began. This understanding is the foundation of our current, standard model of cosmology, known as the lambda CDM model. Lambda stands for the cosmological constant, and CDM for cold dark matter. This model has been remarkably successful, and it aligns with many other things we see in the universe with astonishing precision. One of the strongest pieces of evidence is the cosmic microwave background, CMB*. This is the faint, ancient afterglow of the Big Bang. Satellites have mapped this light in exquisite detail, revealing tiny temperature fluctuations which were the seeds of all cosmic structures. The lambda CDM model perfectly predicts the pattern of these subtle hot and cold spots. Another powerful line of evidence comes from baryon acoustic oscillations, BAO*. In the early universe, sound waves rippled through the hot, dense plasma. When the universe cooled, these waves were frozen in place, leaving a characteristic pattern, a sort of preferred distance between galaxies. The Dark Energy Spectroscopic Instrument, DESI, has created the largest 3D map of the universe to date by measuring the positions of tens of millions of galaxies to trace these patterns, and its results have confirmed the predictions of the lambda CDM model with incredible accuracy. This model, supported by so many different kinds of observation, tells a powerful and consistent story. It is the reigning explanation in cosmology. But it also predicts a very specific, and rather bleak, final fate. If dark energy is truly a constant, the acceleration will continue forever. This leads to a future known as the Big Freeze, or heat death, As space expands ever faster, distant galaxies will be pushed away from us faster than the speed of light, their light no longer able to reach us. They will vanish from our sky, crossing a cosmic horizon beyond which we can never see them again. Our cosmic neighborhood will become an island in an endless void. Over trillions of years, the gas clouds in our local group of galaxies will be used up, and star formation will stop. The existing stars will one by one burn out and die. The universe will become a dark, cold place filled with stellar remnants. Over almost unimaginable timescales, even these remnants will decay. Protons may dissolve, and supermassive black holes will slowly evaporate through Hawking radiation. The end result is a universe that is almost perfectly empty. A cold, dark, and dilute soup of particles stretched across an incomprehensible expanse, where the temperature is near absolute zero. A universe where nothing ever happens again. This is the fate predicted by the lambda CDM model. A cold, lonely, and eternal end. For decades, this has been the accepted, if grim, final chapter. But what if the story is about to change? A quiet rebellion, cracks in the cosmic story. For all its success, the lambda CDM model rests on one crucial idea: that dark energy is constant, unchanging through all of cosmic time. But what if it isn't? What if this mysterious influence evolves, weakens, or changes its nature? For years, this was a fringe idea. But recently, a series of quiet clues have emerged, creating small cracks in the otherwise smooth facade of the standard model. A subtle rebellion is brewing in the heart of cosmology. One of the first signs of trouble is a persistent disagreement known as the Hubble tension. This is a problem with measuring how fast the universe is expanding today. When we use observations of the early universe, like the cosmic microwave background, and apply the lambda CDM model to predict today's expansion rate, we get a value of about 67 km per second per megaparsec. But when we measure the expansion rate more directly, using objects in the nearby universe like supernovae and pulsating stars, we get a different number. Around 73. For years, it was hoped this discrepancy would disappear as our measurements improved. But with new data from telescopes like the James Webb Space Telescope confirming the local measurements, the tension has not gone away. It has become a serious question, suggesting that either our measurements have a hidden flaw, or the lambda CDM model that connects the early and late universe is incomplete. This has opened the door to other ideas. What if dark energy isn't a constant, but a dynamic field that changes over time, a concept known as quintessence. Unlike a constant, quintessence could have its strength vary as the universe evolves. And recently, the Dark Energy Spectroscopic Instrument, or DESI, added another layer to the story. While its primary data has been highly consistent with the constant nature of dark energy, some analyses that combine DESI's map with other cosmological data have shown subtle hints that dark energy might not be perfectly constant. The evidence is not yet strong enough to be decisive, but it has made cosmologists look closer and consider that the story might be more complex. This brings us to a newer, more radical idea, one that questions the very foundation of the dark energy discovery itself. A team of astronomers, led by Young Wook Lee at Yonsei University, took a fresh look at the type Ia supernovae. The whole idea of using them as standard candles relies on the assumption that a supernova that exploded 7 billion years ago is the same as one that explodes today. But the Yonsei team asked a simple question. What if the age of the star that explodes affects the brightness of the supernova? Through careful analysis, they found evidence for what they call a progenitor age bias. They suggested that supernovae from younger stars in the distant universe might be intrinsically a bit dimmer than those from older stars nearby. This is a profound challenge. We thought those distant supernovae were fainter because they were farther away due to acceleration. But what if they were just fainter to begin with? When the team corrected the data for this proposed age bias, the evidence for cosmic acceleration seemed to disappear. Their model suggests the universe may have already entered a phase of deceleration. It is important to say, this is an idea that is still very new and controversial. It sits outside the mainstream consensus, which remains strongly supported by a great deal of other evidence. But it shows how science works by constantly re-examining its own foundations. On one side, we have the established story of lambda CDM, predicting an endless, accelerating expansion. On the other, a quiet rebellion, fueled by the Hubble tension and now a direct challenge to the supernova evidence itself. The fate of the universe hangs in this quiet uncertainty, poised between two very different destinies. The final chapter, two possible endings. The quiet debate between these two cosmic stories. A universe with a constant dark energy versus one where this influence is fading, is not just an academic one. It dictates the very end of time. The final chapter of reality has two possible drafts, and scientists are working right now to figure out which one might be true. Ending A. The reign of dark energy and the Big Freeze. First, let us consider the story where the new clues turn out to be subtle errors, and the lambda CDM model remains the best description of our universe. In this future, dark energy is a constant, relentless pressure pushing spacetime apart. The fate is the one we have come to accept, the Big Freeze. It is an end of profound and poetic loneliness. Imagine standing on a world billions of years from now, looking at the night sky. Instead of a tapestry of countless galaxies, you would see only the stars of our own Milky Way, gravitationally bound to our local neighbors. Every other galaxy in the universe would have been pushed beyond our cosmic horizon, their light gone forever, as if they had never existed. The universe beyond our small island would have become an inaccessible void. The timeline of decay would continue. Within our isolated island, star formation would slow to a stop as the reserves of gas were used up. One by one, the lights would go out. Trillions of years would pass. The universe would become a silent, dark expanse, populated only by cold, dead stellar remnants. Over timescales that defy comprehension, even these would fade away as black holes evaporate and matter itself may dissolve. This is the ultimate triumph of dark energy. Not a violent victory, but a slow, quiet conquest ending in a perfect, eternal stillness. A universe where nothing happens, and nothing ever will happen again. An infinite expanse of cold, dark silence. This is the fate we seem locked into if dark energy is constant. Ending B. The fading of dark energy and the great unknown. Now, let's entertain the other possibility. What if the hints are real? What if dark energy is weakening, or was never what it seemed? If this is true, the final chapter is torn up. The future becomes a thrilling, and perhaps terrifying, unknown. If dark energy is a dynamic field that is losing its strength, the cosmic story takes a dramatic turn. For billions of years, dark energy has been winning. But now, its power is fading. Gravity, the patient, ever-present force, begins to regain its influence. The cosmic acceleration slows, halts, and could eventually reverse into deceleration. What happens next depends on how quickly dark energy fades. One possibility is a scenario known as the Big Crunch. With dark energy gone, gravity becomes the master of the cosmos again. The expansion of the universe stops and then reverses. Galaxies begin rushing toward one another. The end would be a mirror image of the Big Bang, as the universe collapses into an infinitely hot, dense singularity. Some theories even suggest this could lead to a big bounce where the collapse triggers a new Big Bang, creating a new universe in a quiet, eternal cycle. Another, more exotic possibility is the Big Rip. This could happen if dark energy, instead of weakening, were to grow stronger over time. In this case, the repulsive force would become so powerful it would overcome everything. It would tear galaxies apart, then solar systems. In the final moments, it would overcome the forces holding atoms together, and spacetime itself would be pulled asunder. The discovery that dark energy might be evolving opens these and other possibilities. We may not be heading for a slow fade, but for a fiery collapse or a violent tearing apart. The key takeaway is uncertainty. The moment we admit dark energy might not be constant, the certainty of our fate evaporates. The end of the universe is no longer a settled question. It is an open, active field of research, and the answer is out there, waiting. We are living in a revolutionary time for cosmology. We stand at a precipice of understanding, looking into the deep mystery of cosmic destiny. For a while, we thought we had the final page of the story, a tale of endless expansion and a quiet, cold end. But science is a story of constant revision, of challenging what we think we know. The faint light from distant stars, the ancient echoes in the cosmic microwave background, and the delicate map of galaxies are the places we look for answers. The quiet tensions in our measurements and the new, challenging ideas are not signs of failure, they are the thrilling signs of progress. They are clues that point toward a deeper, more complex truth than we ever imagined. Is dark energy a constant, its victory preordained, leading us toward the silent cold of the Big Freeze? Or is it a dynamic, fading power, soon to yield to gravity's relentless pull, perhaps leading to a fiery Big Crunch and the rebirth of the cosmos? We do not yet have the final answer. But for the first time, we have the tools to search for it. The next generation of telescopes will map the universe with even greater precision, testing these rival stories. They will decide the outcome of this quiet cosmic contest. The final chapter of the universe is being written right now, not in the stars, but here on Earth, in the minds and machines of those who dared to ask the biggest questions of all. The mystery is what keeps us going. And whatever the answer may be, the quest to find it is the grandest adventure of our time. If you're fascinated by the grand mysteries of our cosmos and want to stay on the front lines of discovery, consider subscribing and joining us on our journey to the very edge of knowledge. The universe is full of stories waiting to be told. I watched the last star in the universe die. There is a silence at the end of things. For more than 1 trillion years, there has been nothing but this. A single, quiet observer, and that one last light. It has no name. It is the final star in the universe. And my purpose is to watch it fade. There is no clock, no calendar to mark the passing of time. Time is measured now only by the slow, steady dimming of this final ember. The space around is a perfect, featureless black, an emptiness more complete than any night sky ever seen from Earth. The great cosmic story is over. The galaxies have long since receded from one another, their stars going out one by one, like candles in a vast, empty room. First the brilliant, fast-burning blue giants, then the steady yellow suns like our own, and finally, after ages that are difficult to imagine, the stubborn, long-lived red dwarfs. All of them gone, all but this one. It hangs in the distance, a pinprick of deep red light in an eternity of darkness. It is the universe's last memory of warmth, its final, quiet word before the silence becomes absolute. For ages, I have been its only witness. A final consciousness in a universe that has otherwise gone to sleep. My function is simple: to see the story through to its very end. To watch the last light of creation finally surrender to the cold. How we got here. To understand how a universe once filled with a trillion stars could be reduced to this single, fading point, you have to understand one of the most fundamental rules of the cosmos. The second law of thermodynamics. It is a simple but relentless principle. In any closed system, which the universe itself is, disorder, or entropy, always tends to increase. Think of a hot cup of tea left in a cold room. The heat does not stay in the cup, it spreads out, moving into the cooler air until the tea and the room are the same temperature. The useful energy, the difference between hot and cold, is lost to a state of quiet equilibrium. The universe is a bit like that cup of tea, on a much grander scale. It began in the incredible heat and density of the Big Bang, a state of very low entropy. Since then, the universe has been expanding and cooling. In the beginning, this expansion was what allowed everything to form. It allowed energy to cool and condense into particles, then atoms, which gravity then patiently gathered into enormous clouds of gas. Within these clouds, the first stars ignited, and the universe was filled with light. These stars were the engines of cosmic change. In their cores, they forged hydrogen into helium, and in their dramatic deaths, they scattered heavier elements, the carbon, oxygen, and iron needed for planets and for life, across the cosmos. For billions of years, galaxies were vibrant, busy islands of light, with new generations of stars being born as old ones died. Our own Milky Way was just one of countless such places. But the second law of thermodynamics is patient, and its effects are inevitable. The expansion of the universe, driven by the mysterious force we call dark energy, began to stretch the space between galaxies. Over 100 billion years, the sky grew darker. Neighboring galaxies, which had once been close, accelerated away until their light could no longer reach us, vanishing beyond a cosmic horizon. The universe became a collection of lonely island galaxies, each one destined to burn out on its own. Within these isolated galaxies, the material for new stars began to run out. The great clouds of gas and dust were either locked up inside existing stars and their remnants, or had become too spread out for gravity to pull together. Star formation slowed, and then, it stopped. The universe's stellar population began to age, with no new stars to replace the ones that died. The most massive, brilliant blue stars burned through their fuel in just a few million years before exploding. Medium-sized stars, like our Sun, lived for about 10 billion years before swelling into red giants and then shedding their outer layers, leaving behind their hot, dense cores. White dwarfs. These Earth-sized embers no longer made new energy. They simply glowed with leftover heat, slowly cooling over immense stretches of time. But the true survivors, the marathon runners of the cosmos, were the red dwarfs. These small, dim stars are incredibly efficient, sipping their hydrogen fuel so slowly that their lifespans can stretch for trillions of years. Far, far longer than the age of the universe when humanity existed. For a very long time, after every other star had gone dark, These faint red suns were the only lights left, turning the dying universe into a sparse, twilight field. But even trillions of years are not forever. One by one, they too used up their fuel. They did not explode, they simply faded, slowly cooling to become white dwarfs. And then, after an almost unimaginable length of time, they would radiate away their last warmth, becoming what we once theorized but had never seen: black dwarfs. Cold, dark, invisible husks, no longer stars, just gravitational ghosts drifting silently through the void. This was the era I was born into. An age dominated by stellar corpses, white dwarfs, neutron stars, and black holes, scattered through an almost empty universe. The cosmos was dark, cold, and nearly silent. But it was not quite over. For I am watching the very last of these red dwarfs. A cosmic straggler that, by some fluke of its mass and composition, became the final holdout against the darkness. And its long life is finally, quietly, coming to an end. The observation. My existence is one of quiet observation. There is no ship, no station, just a point of awareness. From my vantage point, the star is a single point of light, but my senses are not limited to sight. I can feel its presence, its vital signs, across the vast emptiness. For 1 trillion years, it has been a constant. It is a red dwarf of the lowest possible mass, a star that has used its fuel with near-perfect slowness. Its light has always been faint, a pale cherry-red glow that is more heat than visible light. For most of its life, it was a model of stability, a slow, steady furnace. But in the last few billion years, a short time in its long life, it has begun to change. The first sign was a flicker. Not a twinkle caused by an atmosphere, but a true unsteadiness in its light. The fusion in its core, which for trillions of years had been so reliable, was becoming erratic. The star is running on fumes. The remaining hydrogen is so sparse that the convection currents, which churn the star's interior and bring new fuel to the core, are beginning to falter. Pockets in the core briefly stop fusing, causing the star's light to dip, before pressure builds again and it sputters back. These flickers have become more common. Sometimes the star dims by half, its red glow fading to a dull purple before brightening again. Each flicker is like a muscle spasm, a death throe playing out over millions of years. It feels like watching a candle in its final moments, the flame jumping and shrinking as it consumes the last bits of wax. Its color is also changing. As fusion falters and its surface cools, the familiar cherry red has deepened into a dark, blood red. In its dimmest moments, it is almost entirely infrared, a glow that is felt more than seen. I can sense the composition of its light shifting, the spectral lines of hydrogen growing weaker, a whisper of what they once were. The star is slowly being overwhelmed by its own ash, helium. For a star this small, there is not enough mass to ignite helium fusion, so the helium is just inert waste, clogging the core and choking the fire. The star is also shrinking. As its energy output fades, the pull of its own gravity is slowly winning. This compression heats it, a temporary effect that causes its light to brighten for a few million years, a false spring before the final winter. But it is a losing battle. The contraction cannot restart the stalled fusion. It can only delay what is coming. I am witnessing the slow collapse of the universe's last hearth. There is a profound loneliness to this. In the early eons, there were other lights, other dying red dwarfs scattered across the darkness. One by one, they went out. I remember the last one before this. It faded over 1 billion years until it, too, was gone. For the last 10 trillion years, there has been only this one. Its struggle feels like the last process, the last, something happening, in a universe that is giving in to stillness. Everything else is static and cold. Black dwarfs drift unseen, neutron stars spin down, and even the supermassive black holes at the hearts of long-dead galaxies are so far away that they are effectively in different universes. All of existence, all of the remaining cosmic activity, is contained in this single, sputtering point of light. It pulses. A slow beat that takes 1,000 years to complete. A surge of light, then a long, slow fade. It is the last heartbeat of the cosmos. Each beat is weaker than the last. The rhythm is slowing. I feel the end approaching. The star has maybe a few million years left. For me, after all this time, that is only a moment. I have watched it for 1,000,000,000,000 years. I can wait for its final breath. It is the only thing left to do. To bear witness. To remember there was light. The climax. In its final million years, the gentle pulse is gone, replaced by chaotic, unpredictable flickers. It flares, sometimes doubling its brightness for a few centuries, using up what little energy it has left. These are not the flares of a healthy star, but the frantic, desperate bursts of a dying one. Each flare is followed by a deeper, longer period of dimming. According to stellar models, the lowest mass red dwarfs do not swell into red giants. Instead, as their hydrogen is used up, they are predicted to grow hotter and bluer for a time, becoming what are sometimes called blue dwarfs. This star is following that path. Its long, slow life is ending not in a violent outburst, but in a quiet, feverish transformation. The deep red light I knew for so long has shifted. Over thousands of years, it has become a brilliant white, and then a piercing, electric blue. It is an unnatural glow against the perfect black, the universe's swan song. For a few centuries, it shines with the light of 1,000 of its former self, burning away the last of its life in a final, quiet blaze. Then, the final dimming begins. Not a flicker, but a steady, unstoppable decline. The blue light softens to white. The white fades to a pale, ghostly yellow. The yellow cools to a dull orange, and then back into the deep, sullen red of its long twilight. The process is now happening on a timescale I can perceive year by year, then month by month. In the final hours, it is a barely visible point of dark red light. It gives off almost no visible light, only a faint trace of heat that I can feel fading across the emptiness. The last heartbeat is over. The last breath has been drawn. It hangs there, a dying coal in a cosmic fireplace. I focus my entire awareness upon it. This moment is the end of light, the end of heat, the end of change, and then, it is gone. It does not wink out. There is no final flicker. The light is simply no longer there. One moment, a single, tiny point of warmth and memory. The next, only blackness. The darkness is total. It feels like a physical presence, a heavy blanket that smothers everything. The void before was empty, but it was punctuated. Now, there are no more punctuations. It is a sentence with no words, an existence with no features. The silence is what truly changes. Before, there was the noise of the star, its radiation, its gravitational whisper. Now, that too is gone. The silence is no longer an absence of sound, it is the presence of absolute stillness. It is the sound of a universe that has finally, completely, stopped. I am alone, utterly alone in an infinite, lightless, heatless tomb. The last star is dead. The age of stars is over. The silence and the void. Time itself seems to stop. There is no before and after, only a continuous, unchanging now. My consciousness remains, a solitary island of thought in an ocean of nothing. Without the star, I have no external reference point. I am adrift in what was long thought to be the final state of the universe, the heat death. A state of maximum entropy, where everything has reached the same temperature and no work can be done. But science, like life, is a process of revision. For a long time, it seemed that the universe would expand forever, leading to this cold, quiet end. Yet, recent observations from projects like the Dark Energy Spectroscopic Instrument have suggested that dark energy might not be constant. It may be weakening. If this is true, the story might not end with an endless freeze. The expansion could slow, stop, and one day reverse, pulling everything back together into a Big crunch. Perhaps 20 billion years from now. The universe's end, it turns out, was never as certain as we thought. For now, though, the darkness holds. Out there in the void are the black dwarfs, the cold corpses of stars. There are neutron stars, spinning down, and black holes. For an age that makes the era of stars feel like a brief moment, the black holes are the only active things left, slowly sweeping up any matter that drifts too close. But even they are not eternal. As Stephen Hawking first proposed, black holes are thought to evaporate. Through a quantum process, they leak faint radiation, losing mass over immense timescales. For a supermassive black hole, this process could take a Google years, 10 to the power of 100, an amount of time so large it is difficult to describe. From my silent place, I can sense this new, even slower era, as the last organized structures in the universe slowly dissolve, particle by particle, into the void. After the last black hole has evaporated, only one quiet question remains. Is matter itself stable? Some theories, known as grand unified theories, suggest that even protons are not truly fundamental and might decay over time. Though it has never been observed, this process is predicted to take at least 10 to the power of 34 years. If it happens, the cold black dwarfs would begin to unravel. Matter itself would dissolve into a thin, featureless soup of particles. By the time this is complete, the universe would be a void in the truest sense. An almost infinitely large, cold, and empty space, with particles spread so far apart they would never interact again. No light, no heat, no matter, no structure. What was the point of it all? The brief flash of creation, the galaxies, the stars, the intricate dance of life? What is the meaning of a cosmos that flourishes and then dies, leaving nothing behind but an eternal, empty silence? There is no one to provide an answer. I am the last question, in a universe with no more answers. There's also something quietly humbling in a final thought experiment from early physics, the Poincaré recurrence theorem. It suggests that in a truly infinite time, any system could spontaneously return to a previous state. Perhaps, after a time so vast it makes the lifetime of a black hole seem instant, a new universe could emerge from random quantum fluctuations. The timescale for such an event is so remote, sometimes estimated as 10 to the power of 10 to the power of 56 years or more, that it is functionally the same as infinity. It is a hope so small it is almost indistinguishable from despair. So I wait. I exist. In the profound, absolute silence. The light is gone. The story is over. There is nothing left to watch. There is only the dark. And so, the vigil continues in the cold and the quiet. The final chapter of light has been written, the last page turned. What remains is a testament to the awesome, indifferent, and perhaps temporary, nature of everything. A universe that was once a symphony of light and life has faded into a single, silent note, held for what may, or may not, be eternity. The sleep story of how a star dies. For as long as there have been eyes to see, there has been the night sky. A quiet, dark ceiling holding countless points of light, each one a distant sun living out a story written in physics and deep time. Some burn with a furious, blue-white intensity. Others glow with a steady, yellow calm. Many have already vanished, their light still traveling across the vastness of space, a final message from a world that no longer exists. This is a journey to witness the end of those stories. Not as myths or portents, but as real physical events, shaped by gravity, pressure, and time. All of them stretch the idea of what an ending can be. Welcome. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether in a city, a forest, or somewhere quiet in between, feel free to share where you are listening from, under that same sky. For now, there is nothing else to do but let the world outside fall away. Find a position that feels settled. Let your breathing find its own quiet rhythm. Each breath is an anchor, a reminder that your body is here, in this moment, ready for rest. With every exhale, imagine sinking a little deeper, as if your awareness is beginning to drift upward, leaving the room behind. Floating past the ceiling, into the cool night air, rising until the world below is just a soft, distant hum. You are a silent observer in the vast, quiet dark, and our story is ready to begin. Let us begin our journey with a star much like our own sun. For billions of years, it has held its place in the galaxy, performing a quiet, constant miracle in its core. It has spent the vast majority of its life in a state of perfect balance. In its heart, it fuses hydrogen into helium. This process creates a steady outward pressure of light and heat, a constant push that perfectly balances the immense inward pull of its own gravity. A star's entire life is this delicate dance between pressure pushing out and gravity pulling in. For billions of years, this star has danced perfectly. It has been a dependable fire in the hearth of its solar system. Its light has been constant, a beacon of stability in the endless night. But nothing, not even a star, burns forever. After some 10 billion years, the hydrogen fuel in the star's core begins to run out. The fire in the very center is exhausted, leaving behind an inert core of helium ash. Without the outward pressure from fusion, gravity, patient and relentless, begins to win the dance. The core of the star, no longer supported, starts to collapse under its own colossal weight. This collapse is the beginning of the end. But it is not a violent or sudden event. It is a slow, majestic, and in its own way, beautiful transformation. As the helium core contracts, it becomes incredibly hot. This intense new heat radiates outward, igniting a shell of hydrogen that surrounds the core. This new fire, happening in a shell rather than the center, is far more powerful than the star has ever known. It generates a tremendous amount of outward pressure, pushing the star's outer layers into a slow, inexorable expansion. This is the beginning of the red giant phase. Over millions of years, the star swells to 100, then 200 times its original size. If this were our sun, its fiery edge would swallow Mercury, then Venus, and boil away the oceans of Earth. But from our safe distance, there is no fear, only a sense of cosmic awe. As the star expands, its energy is spread over a vast, bloated surface. This causes the surface to cool, its color shifting from a brilliant yellow-white to a deep, dusky red. It has become a red giant. It is no longer a steady point of light, but a magnificent, swollen ember. From the outside, it appears majestic and serene. A giant, silent lantern hanging in the void. For a time, the star remains in this state. Inside, its helium core continues to contract and heat up until a new miracle occurs. The helium ash, once inert, suddenly ignites, fusing into carbon and oxygen. The star has found a second life, a new source of fuel. This brings a temporary stability, and the star shrinks slightly. But helium is a less efficient fuel, and it will be consumed much, much faster. After a few million years, the helium is also exhausted. The core is now made of carbon and oxygen ash. For a star of this size, there is not enough mass to ignite the carbon. The fires are going out for good. The star now enters its final, most peaceful stage of letting go. In its last throes, it begins to gently pulsate like a slow, cosmic heartbeat. With each pulse, it pushes its outer layers away. This is not a violent explosion. It is more like a series of gentle puffs, releasing great, smoky shells of gas into space. As these layers of gas drift away, the hot, tiny core of the star is finally revealed. It is incredibly hot, blazing with intense ultraviolet radiation. This fierce light shines into the expanding clouds of gas the star just shed, causing them to glow with breathtaking colors. Hydrogen glows a vibrant red. Oxygen glows a spectral green and blue. This glowing, expanding shroud is called a planetary nebula. The name is a mistake. Early astronomers, looking through small telescopes, thought these round, glowing clouds looked like planets. They have nothing to do with planets. They are the final, beautiful sigh of a dying star, a unique masterpiece of rings, bubbles, and intricate, lacy filaments. The material in these nebulae, carbon, nitrogen, oxygen, is scattered into the thin gas between the stars. It becomes the raw material for a new generation of stars and planets yet to be born. Every ending is a new beginning. And at the center of this glorious, fading spectacle is what remains: a white dwarf. It is all that is left of the core, a sphere roughly the size of the Earth, containing nearly the entire mass of the original star. The density is almost unimaginable. A single teaspoon of its material would weigh as much as an elephant. Gravity has crushed the atoms so tightly that physics itself prevents the star from collapsing any further. It is a solid, crystalline object, like a giant diamond in the sky composed of carbon and oxygen. The white dwarf no longer produces new energy. It is a stellar remnant. It glows not because it is burning, but because it is still hot, like a coal taken from a fire. And so it begins the longest, quietest phase of its existence, cooling down. For billions, even trillions of years, it will simply radiate its remaining heat into space, slowly fading from white, to yellow, to orange, to red. The universe is not yet old enough for any white dwarf to have completed this journey. But in the distant future, it will have radiated away all its heat, becoming a cold, dark, invisible black dwarf. A stellar ghost, drifting silently through the eternal night. Not a violent end, but a slow, graceful fade to black. A perfect, final piece. Not all stars, however, are destined for such a quiet end. The life and death of a star are written in its mass. The story we have just followed is for stars like our Sun. But what of the giants? What of the stars born with 8, 10, or even 50 times the mass of our Sun? Their lives are very different. They live fast, shine brilliantly, and die young. While a star like our Sun lives for 10 billion years, a massive star might live for only a few million. They burn through their fuel at a ferocious rate, shining with a blinding blue-white light. When their hydrogen is exhausted, they swell into red supergiants, so vast they would engulf the orbit of Jupiter. Because of their immense mass, their cores can fuse elements far beyond helium. Carbon fuses into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. The core becomes a cosmic onion with layers of different elements all fusing at once. But with iron, the process stops. Fusing iron consumes energy instead of releasing it. The iron core is the ultimate ash. It cannot burn. In an instant, the outward pressure that supported the star vanishes. Gravity wins. The collapse is sudden and catastrophic. In less than a second, the core collapses from the size of the Earth to a ball only a few miles across. The star's outer layers come crashing down at a quarter of the speed of light, bounce off the super-dense core, and create a shockwave of unimaginable power. This shockwave rips the star apart in an explosion known as a supernova. For a few weeks, this single exploding star can outshine its entire galaxy. The explosion forges all the elements heavier than iron, gold, silver, platinum, uranium, and blasts them into space. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it was created in the cores of stars and scattered by these great explosions. We are, in the most literal sense, made of stardust. After the brilliant light of the supernova fades, what is left behind? If the star was massive, but not a true titan, the collapsed core survives as a neutron star. Here, gravity has crushed protons and electrons together to form a ball of pure neutrons perhaps only 12 miles in diameter, yet containing more mass than our Sun. It is the densest object in the universe we can still theoretically see. But for the most massive stars of all, nothing can stop the pull of gravity. The core collapses completely, crushing itself down into an object with zero volume and infinite density, a singularity. This singularity warps the fabric of space and time so completely that it creates a region from which nothing, not even light, can escape. It has become a black hole. A black hole is not a hole in the sense of being empty, but the opposite, an unimaginable amount of matter in an impossibly small point. It is gravity's final victory. A different kind of peace. A place of absolute stillness. And so, we drift back. Away from the silent, glittering diamond of the white dwarf. Away from the ghost of the supernova, and the deep quiet of the black hole. We drift back through the endless ocean of stars, each with its own story, its own destiny. We see the beautiful, glowing clouds of nebulae where the ashes of dead stars are gathering, ready to begin the cycle anew. The cosmos is a place of endless transformation. Death is not an end, but a transition. We drift back towards that familiar blue and white marble. Back towards home, back towards your room. As you settle back, bring with you the peace of the cosmos. The peace of long, slow cycles. The story of the star reminds us that evolutionary importance is not measured by how impressive a thing appears, but by how it transforms what comes after. The quiet star leaves behind the building blocks of life. The giant star forges the elements of worlds. Each ending serves a purpose. There is nothing more to think about. The journey is over. It is time for rest. Surviving 100 Google years to see the final explosion. The universe is around 13.8 billion years old. It's a number so large it feels like an eternity. Our minds struggle to grasp the quiet distance that separates us from the first moment of creation. But what if this entire span of time, from the Big Bang to this very moment, is just a single second in a much longer story? What if the age of everything we know is almost zero compared to the timeline we are about to walk? Today, we are not just going to the end of time. We are going to survive it. We will journey forward, past the fading of the last star, past the slow decay of matter itself, for 100 Google years, to witness the final, lonely flash at the very end of everything. This is a quiet journey to the ultimate heat death of the universe, a trip to see the cosmos draw its last, slow breath. Leaving the age of stars. Before our journey can truly begin, we must first say goodbye to the light. We live now in what is called the Stelliferous Era, the age of stars. It is a brilliant, beautiful, and deeply temporary time. The night sky, glittering with the fires of countless nuclear furnaces, is the defining feature of our universe. But like all fires, they must eventually fade. The first to go will be the giants. The brilliant blue, massive stars, hundreds of times the mass of our sun, live fast and die young. They burn through their fuel in a cosmic moment, lasting only a few million years before they end in a brilliant flash. They are the artists of the cosmos, seeding the void with the heavy elements needed for planets and for life, but their time is fleeting. Next are the stars like our own sun. They are more conservative with their fuel, enjoying a stable life for billions of years. Our sun is about halfway through its 10 billion year lifespan. In another 5 billion years, it will swell into a red giant. Mercury and Venus will be consumed, and the Earth will be scorched into a quiet, lifeless cinder. Afterwards, the sun will puff away its outer layers, leaving behind its cooling, dying core, a white dwarf. Across the universe, trillions of sun-like stars will follow this same path. One by one, their light will be extinguished, and their planetary systems will be cast into darkness. For a time, the universe will still have light, but it will be a different kind of light. The cosmos will be dominated by the dim, ruddy glow of the most common and longest-lived stars, the red dwarfs. These tiny, efficient stars make up the vast majority of the stellar population. They are the quiet survivors of the cosmos, sipping their hydrogen fuel so slowly that their lifespans can stretch for trillions, and in some cases, up to 100 trillion years. Because the universe has only been here for about 13.8 billion years, not a single red dwarf has yet reached the end of its life. They are all, in a cosmic sense, still infants. But our journey is long, and we will wait for them. We will watch as, for trillions of years, these tiny red embers are the only beacons in a growing darkness. They will be the last refuge for any form of life that might have survived this far, huddled around their faint warmth. And yet, even their incredible longevity is not infinite. Around 10 to 100 trillion years from now, the very last red dwarf will finally use up its hydrogen. Unlike a massive star, it will not go out with a bang. It will simply fade. Its nuclear heart will stop, and its ruddy light will dim, cool, and die. It will become a silent, cold white dwarf, joining the ever-growing graveyard of stellar remnants. With the fading of this last, lonely star, the Stelliferous Era ends. The age of light is over. The universe as we know it, a place of shining stars and glowing galaxies, is gone. We are now entering the Degenerate Era, and the true quiet is just beginning. The Degenerate Era and the long wait. Imagine a universe without stars. The idea is unfamiliar to us, for whom the stars are a symbol of permanence. But now, 100 trillion years in the future, the cosmos is a pitch-black expanse, populated only by the dead. This is the Degenerate Era, named for the degenerate matter that makes up its main inhabitants: white dwarfs, neutron stars, and black holes. These are the compressed corpses of the stars that once lit up the sky. Galaxies still exist, but they are not the glowing spirals we see today. They are ghost galaxies, vast, dark collections of stellar remnants, slowly orbiting a central supermassive black hole. The planets that once orbited these dead stars are still there, but they are frozen worlds, long ago flung into new orbits or consumed by their dying suns. Over unimaginable time, gravity will continue to shape these phantom galaxies. Stellar remnants will be ejected into the lonely void, while others spiral inward, finding their final resting place in the grip of the central black hole. The universe is not completely dark. There is the occasional flicker. When two white dwarfs spiral into each other and merge, they can trigger a final, brief flash of light in the unending night. Collisions between brown dwarfs, or failed stars, might now and then produce a new, temporary red dwarf that burns for a few trillion years before it too fades. But these events will become rarer and rarer as the universe expands, its contents growing more distant and diffuse. For a period of time that our minds cannot really hold, this is the state of the universe. A cold, dark, quiet place, filled with the ghosts of stars. But even these ghosts are not eternal. A strange and theoretical process is beginning its slow work on them, a process that will eventually dissolve the very fabric of matter. This is the era of proton decay. According to our current understanding of particle physics, protons are perfectly stable. But many theories that try to unite the fundamental forces of nature suggest that this stability might not be absolute. These theories propose that over immense timescales, protons can decay into lighter particles. This process is staggeringly rare. The predicted half-life of a proton is, at a minimum, somewhere around 10 to the power of 34 years. For comparison, the universe so far has only existed for a tiny fraction of that time. But on our journey, we have nothing but time. We watch as this slow chemistry begins its work. The stellar corpses of the Degenerate Era, the white dwarfs and neutron stars, are made of ordinary matter. One by one, over a span of time that makes the age of stars seem like an instant, these particles will begin to dissolve. Imagine a white dwarf, a crystal sphere of carbon and oxygen the size of Earth but with the mass of the Sun. For trillions of millennia, it has been a cold, dark object. Now, its very substance begins to unravel. A proton inside a carbon nucleus winks out of existence, replaced by a faint flash of radiation. Then another. And another. The process is agonizingly slow, but its effect is absolute. The solid matter of the dead star breaks down, its structure failing, its mass slowly converting into a diffuse cloud of energy. This is the fate of all ordinary matter. Planets, moons, asteroids, and the stellar remnants themselves will all slowly disintegrate. The process is a gentle, patient erasure of reality. By 10 to the power of 40 years, the last white dwarf will have evaporated into nothing. What remains? A universe that is almost entirely empty. The grand structures of the cosmos are gone. The very atoms that built them are gone. All that is left is a thin, featureless soup of stray photons, neutrinos, and other particles, wandering through an ever-expanding, ever-cooling void. And, dotted throughout this void, are the only objects to survive the death of matter itself. Black holes. We have now reached the end of the Degenerate Era. Matter as we know it has ceased to exist. The universe belongs to darkness and to these silent, gravitational survivors. We are entering the black hole era, the final age of cosmic structure, and our journey is nearing its most important moment. The black hole era and the final countdown. We have traveled 10 to the power of 40 years into the future. The universe is an unrecognizable void. The last star has been dead for trillions of years. The very protons that formed the bedrock of reality have decayed into a whisper of radiation. All that remains are the objects that have outlasted everything, black holes. This is the black hole era. For an age, these objects grew, swallowing stars and gas during the Stelliferous Era and the remnants of dead stars during the Degenerate Era. The supermassive black holes at the hearts of what were once galaxies now contain the mass of billions, or even trillions, of suns. They are the universe's final and most enduring structures. And yet, they are not eternal. Even these titans of gravity are destined to fade. Their fate was first understood not by Einstein, but by Stephen Hawking. In the early 1970s, Hawking was wrestling with an idea. According to general relativity, the event horizon of a black hole, its point of no return, could never shrink. This reminded him of the second law of thermodynamics, which states that the disorder of a system can never decrease. This similarity led Hawking to a revolutionary thought. What if black holes weren't completely black? What if they could radiate? By combining general relativity with quantum mechanics, Hawking discovered something astonishing. Empty space, he realized, is not truly empty. It is a quiet murmur of virtual particles, pairs that pop into existence for a moment before annihilating each other. This happens everywhere, but what happens when it occurs right on the edge of a black hole's event horizon? Hawking reasoned that it would be possible for one particle of a pair to fall into the black hole, while its partner escapes. The escaping particle appears as real radiation. To an outside observer, it looks as though the black hole itself is faintly glowing. This became known as Hawking radiation. For the laws of physics to remain balanced, the energy for this new particle has to come from somewhere. It comes from the black hole itself. The net effect is that the black hole slowly loses mass. It is, in a sense, evaporating. The process is almost impossibly slow. The rate of a black hole's evaporation is inversely proportional to its mass. This means the bigger the black hole, the colder it is, and the more slowly it evaporates. A black hole with the mass of our Sun would take an estimated 10 to the power of 67 years to evaporate completely, a number so vast it is difficult to describe. The supermassive black holes, which now rule the universe, will last even longer. A black hole with the mass of a billion suns will take around 10 to the power of 94 years to disappear. The very largest could last for up to 10 to the power of 100 years, a number known as a googol. This is the timescale of our journey. So, we wait. The eons pass by in a silent, featureless stream. The universe continues to expand, becoming colder and emptier. The black holes are the only active things left, and their activity is a slow, patient, almost imperceptible leak of energy into the void. The smaller black holes are the first to go. After some 10 to the power of 67 years, they begin the final phase of their life. As a black hole loses mass, its temperature increases, and its rate of evaporation accelerates. What began as a slow trickle of photons becomes a steady stream, and then a torrent. In its final moments, the black hole is no longer cold and black. It is blazing hot. In the last second of its life, a stellar mass black hole unleashes a final, brilliant flash of high-energy radiation before vanishing completely. For a brief moment, there is a burst of light in a universe that has known only darkness for eons. Then, silence returns. One by one, across the impossibly vast canvas of space-time, the remaining black holes begin this final countdown. The slightly more massive ones follow, then the intermediate ones. Each one ends its life in an identical burst of energy, a final quiet roar against the encroaching silence. We are now approaching the year 10 to the power of 100. A Google years have passed. The universe is now so old and so expanded that the distance between particles is astronomical. Almost all the black holes have evaporated, but not all of them. Somewhere, in the unending darkness, one remains. The last one. It was once the supermassive heart of a colossal galaxy cluster. It is the most massive black hole that ever existed, and for that reason, it is the last survivor. But its time is now up. After a Google years of silent reign, its mass has dwindled, its temperature has risen, and its end is upon us. We have traveled to the end of everything to witness this. The final explosion and the dark era. We have arrived. The year is 1 followed by 100 zeros. A Google. The time that has passed since the Big Bang is a forgotten moment in an ancient past. We are in a universe that is functionally infinite in size and infinitesimally close to zero in temperature. It is a perfect, featureless vacuum. But it is not completely empty. Before us hangs the last macroscopic object in existence. It is the ghost of a supermassive black hole. Once a titan holding the mass of 100 trillion suns, it has spent a Google years slowly bleeding its substance back into the cosmos. Now, in its final stages, it is no longer a region of darkness. It is a blazing sphere of pure energy. As its mass has decreased, its temperature has risen. The slow leak of photons has become a furious, accelerating torrent. In its final seconds, the process reaches a crescendo. The black hole, now no bigger than an atom, is radiating away the mass of mountains every nanosecond. And then, it happens. In the last fraction of a second, the event horizon collapses. The singularity is exposed. The laws of physics as we know them break down. The remaining energy is released in a single, final burst. A flash of gamma rays more brilliant than a million supernovae erupts into the void. It is the last great event of our universe. The final firework. The light from this final explosion travels outwards, a spherical shell of radiation expanding into the abyss. It will travel forever, its waves stretching and cooling as the universe expands, but it will never encounter another object. There is nothing left to encounter. With that final, silent flash, the black hole era is over. The last complex structure in the universe is gone. We have entered the final age of the cosmos, the dark era. What is the universe now? It is a near-perfect vacuum, unimaginably vast and cold. Drifting within it is a diffuse, vanishingly thin gas of leftover particles. Photons, neutrinos, electrons, and positrons. These are the ashes of a cosmos that once teemed with stars and life. The particles are so far apart they will almost never interact. They are simply adrift in an endless, empty, and expanding night. This is the ultimate fate of the universe. A state known as heat death. It is not an event, but a final, permanent condition. The universe has reached a state where all energy is evenly distributed. This means no more work can be done. No more processes can occur. No more change is possible. Heat death is not a fiery end, but the cold, quiet end of everything. It's the point where time itself becomes meaningless, because there are no events to mark its passage. The universe will simply be a silent, empty, cold, and unchanging void, stretching on for an eternity that truly is an eternity. The story of the cosmos is over. A reflection on meaning. We have done it. We have survived 100 Google years and witnessed the final whisper of the cosmos. We have watched the last star fade, seen the atoms of reality dissolve, and stood before the final evaporation of the last black hole. We have seen the universe descend into the dark era, an eternal, silent void. It is a sobering, even humbling, vision. To see everything we have ever known, every star, every galaxy, ultimately erased. It can leave you with a sense of meaninglessness. If the ultimate fate of the universe is a cold, empty nothingness, then what was the point of it all? But perhaps that is the wrong way to look at it. Perhaps the meaning is not in the destination, but in the journey. The universe, for a brief but glorious time, was not empty. It was filled with light and wonder. It produced stars that forged elements, planets that could hold life, and minds that could look at the sky and ask, why? For a fleeting moment in the grand story, the universe was aware of itself. And what of the information? The story of every star, every planet, every life? Did it all just vanish? Here, Stephen Hawking offered a quiet glimmer of hope. He suggested that information is not destroyed by a black hole, but is stored on its event horizon and then subtly imprinted onto the outgoing Hawking radiation. It is scrambled, almost impossibly so, but in principle, it is not lost. This suggests a profound idea: that nothing is ever truly erased. The energy and information that made up our world, our sun, our bodies, was not destroyed. It was returned to the universe in that final flash. It now roams the dark era as scattered particles, carrying the ghost of a story, a complex pattern that encodes the memory of a universe that once was. Our journey to the end of time does not have to be a story of loss. It can be a story of perspective. The incredible vastness of the future highlights how precious the now is. The existence of consciousness, however brief, in a universe destined for an eternity of silence is not a cosmic joke. It is a quiet miracle. The value of a symphony is not diminished by its final note. The beauty of a life is not erased by its end. And the meaning of our universe is not invalidated by its ultimate fate. It is defined by the fact that it existed at all. That for a time, it was a place of warmth and light, a stage for the extraordinary drama of existence. And that is a story worth telling, even if, in the end, there is no one left to hear it. If this quiet journey into time gave you a new perspective, consider subscribing and joining us again. These ideas are vast, so feel free to share your thoughts in the quiet space below. And if this story is one you feel is worth sharing, we would be grateful. When the universe ends, could time run backwards? Our understanding of the universe's story has a well-established beginning. But what if its ultimate end is not a conclusion, but a new beginning unfolding in reverse? What if the final contraction of our universe compels time itself to flow backward, causing everything we have ever known to replay in the opposite direction? This is not merely a thought experiment. It is a possibility rooted in the fundamental laws of physics, a potential outcome of the universe's ultimate fate. For decades, the prevailing view was that the cosmos would end in a long, slow, cold fade into darkness. New evidence, however, is leading to a revision of that final chapter. The universe might not be destined to die quietly, but to end in a cataclysmic collapse so intense it could reset the very fabric of reality. Tonight, we journey to the end of all things, to a moment of immense density and temperature, to explore a question that challenges our understanding of the past, present, and future. The cosmic story so far. To understand the end, we have to begin with the origin. 13.8 billion years ago, our universe came into being. Before that moment, there was nothing our physics can describe: no space, no time, no matter. Then, from a point of extraordinary energy, came the Big Bang. This was not an explosion within space, it was the expansion of space itself. Every point in the observable universe today was once contained within a singularity, a point of extreme heat and density. From that origin, space began to expand, carrying the material for future galaxies, stars, and planets with it. For the first few 100,000 years, the universe was an opaque, hot mixture of fundamental particles and radiation. Its density was such that light could not travel freely. As it expanded and cooled, atoms began to form, primarily hydrogen and helium. The universe then became transparent, allowing the light from that era to travel unimpeded. Today, we can still detect the faint afterglow of this ancient light. It is called the cosmic microwave background, and it provides a picture of the infant universe, an echo of creation that permeates all of space. As the universe continued its expansion, gravity, the persistent force of attraction, began to draw matter together. Over hundreds of millions of years, vast clouds of gas collapsed under their own mass, igniting to form the first stars. These stars then clustered to form the first galaxies. This marked the beginning of a competition between two major forces that defines our universe's evolution. On one side is the initial expansion from the Big Bang, pushing everything apart. On the other is gravity, working to pull everything back together. For much of the 20th century, the ultimate fate of the universe appeared to depend on a straightforward question: which force is stronger? Is the universe expanding quickly enough to overcome its own gravity, or does it contain sufficient matter for gravity to eventually halt and reverse the expansion? If gravity were to prevail, the expansion would one day slow, stop, and then reverse. This scenario was named the Big Crunch. It presents a symmetric vision of the cosmos, one that begins in a fiery singularity and ends in one. For a long time, this was a leading hypothesis for the universe's end. But in the late 1990s, cosmology was revised by a discovery that suggested the universe's expansion was not just continuing, but accelerating. The competition between expansion and gravity, it appeared, involved a third, previously unknown component. The end of an era, the reign of dark energy. In 1998, two independent teams of astronomers were working to measure the expansion rate of the universe. They used a specific type of stellar explosion, a type Ia supernova, as a standard candle. These supernovae are valuable because they all have a similar intrinsic brightness. By measuring their apparent faintness, astronomers can calculate their distance. By measuring the redshift of their light, the degree to which that light has been stretched to longer wavelengths by the expansion of space, they can determine how fast the supernovae are moving away. The expectation was that if gravity was the dominant force on cosmic scales, these distant supernovae should be receding more slowly than predicted, as gravity would be slowing the expansion over time. What they found was the opposite. The data indicated that the most distant supernovae were fainter, and therefore farther away, than they should have been. The only way to account for this was if the expansion of the universe was accelerating. This discovery, which was awarded the Nobel Prize in Physics in 2011, showed that our model of the cosmos was incomplete. It implied the existence of an invisible, repulsive force pushing space apart and overcoming gravity on the largest scales. Scientists named this phenomenon dark energy. Our best measurements indicate that dark energy constitutes approximately 68% of the universe's total energy density. Normal matter, which includes everything from planets to stars, accounts for less than 5%. We reside in a universe dominated by something we cannot see and do not yet understand. The discovery of dark energy changed the prevailing view of the universe's fate. It seemed to render the Big Crunch model obsolete. If this energy was causing expansion to accelerate, gravity would likely never be strong enough to reverse it. This led to a new dominant theory for the end of the universe, the Big Freeze, also known as the heat death. In this scenario, accelerating expansion would carry distant galaxies away so rapidly that their light would eventually be unable to reach us. They would vanish from view, leaving our own Milky Way galaxy as an isolated system in a vast, empty void. Within our galaxy, stars would continue to burn through their fuel and die. Over trillions of years, the universe would grow darker and colder. The last stars would become cold remnants like black dwarfs and neutron stars. Eventually, even these would decay. Supermassive black holes would evaporate through Hawking radiation. The universe would be left as a vast, dark, and nearly empty expanse of scattered, low-energy particles, approaching a state of absolute zero and maximum entropy, a final state where nothing of significance would ever happen again. For over 2 decades, this has been the standard model for the end of the universe. But what if dark energy is not a constant force? What if its influence is diminishing? A new discovery: gravity's potential return. For 20 years, the scientific consensus has been that the universe is driven by a positive cosmological constant and will expand forever. However, science progresses through continuous questioning and the gathering of more precise data. 2 recent projects, the Dark Energy Survey, DE, in Chile and the Dark Energy Spectroscopic Instrument, DESI, in Arizona, have been central to this effort. These observatories represent the work of hundreds of researchers to create the most extensive 3-dimensional map of the universe to date. Their objective is to measure the positions and redshifts of tens of millions of galaxies and quasars with unprecedented accuracy. By charting the distribution of these objects through cosmic time, they can trace the history of the universe's expansion in fine detail. The latest data, based on observations of nearly 15 million galaxies and quasars, has yielded a significant finding. While the results confirm that the universe's expansion is still accelerating today, they also suggest that this acceleration may be slowing down. This subtle change has led to a re-evaluation of our cosmic destiny. Henry Tai, a theoretical physicist at Cornell University, and his collaborators have developed a model that aligns with this new data. Their work suggests that the cosmological constant, a term representing the energy of empty space, may not be constant or positive. Their model indicates that the underlying cosmological constant could be negative. For 20 years, people believed that the cosmological constant is positive, and the universe will expand forever, Tai stated. The new data seem to indicate that the cosmological constant is negative, and that the universe will end in a big crunch. A negative cosmological constant would act as an attractive force. In this new model, the current accelerated expansion is a temporary phase. The universe might be behaving like a stretched object that is still moving outward for a moment, but an underlying tension is already present, preparing to pull it back. Gravity, it seems, may ultimately prevail. The Big Crunch, a theory once thought to be obsolete, has reemerged as a possibility, revived by some of the most precise cosmological data ever collected. The question of how the universe will end is once again open for investigation. The Great Collapse. Anatomy of the Big Crunch. If this new model is accurate, it provides a potential timeline for the future. Henry Tai's calculations, based on the DE and DESI data, suggest the universe could have a total lifespan of approximately 33 billion years. Given that our universe is 13.8 billion years old, this would place us well into its lifespan. The end, in this scenario, is not infinitely distant. The first major event would occur in approximately 11 billion years. At this point, the universe would reach its maximum size, and the cosmic expansion that began 13.8 billion years ago would cease. For a brief cosmic interval, the universe would be static, poised between its past expansion and its future contraction. Then, the reversal would begin. Space itself would start to contract. At first, the change would be imperceptible, but over billions of years, the collapse would accelerate. Galaxies that have been moving away from us would reverse course and begin moving toward us. This would produce a profound change in our sky. We have always observed a cosmological redshift, where light from distant galaxies is stretched as they move away. In a contracting universe, we would see a blue shift. As galaxies approach, their light would be compressed to shorter, bluer, and more energetic wavelengths. The night sky would eventually begin to glow with an intense blue light. The next phase of the collapse, lasting for about 8 billion years, would involve increasing cosmic density. Voids in space would shrink. Galactic clusters would merge. Galaxies would begin to collide at high speeds. As everything is compressed, the temperature of the universe would rise dramatically. The cosmic microwave background, currently just 2.7 degrees above absolute zero, would heat to thousands, then millions of degrees, turning the universe into a cosmic furnace. The radiation would become intense enough to ignite the surfaces of stars before they collide. The stars themselves would be torn apart as they smash into one another. In the final moments, the compression would be so extreme that atoms and even atomic nuclei would be ripped apart, their constituent particles dissolving into a superheated plasma. All known forms of matter would be erased. Finally, all the mass and energy of the cosmos would converge into a single point of zero volume and infinite density. A singularity, the same type of state from which the Big Bang is thought to have originated. At this point, space, time, and the laws of physics as we understand them would break down. According to Ty's model, this final crunch could occur in approximately 20 billion years. This is the story of the Big Crunch. But this final moment of infinite compression raises a profound question. If the end of the universe mirrors its beginning, could the arrow of time be part of that symmetry? The twist. Reversing the arrow of time. We experience time as a constant, forward-moving flow. The past is recorded in memory while the future is open. In physics, however, the nature of time is less straightforward. At the fundamental level, most laws of physics are time-symmetric. The equations governing the motion of a planet or the collision of particles work equally well forwards or backwards. From a purely physical perspective, a video of a glass shattering is as valid as a video of the shards reassembling themselves. The reason we do not observe glasses reassembling is due to a principle of thermodynamics known as entropy. Entropy is a measure of disorder. The second law of thermodynamics states that the total entropy of an isolated system, like the universe, can only increase or stay the same. An intact glass is an ordered, low-entropy state. A shattered glass is a disordered, high-entropy state. This one-way progression from order to disorder is what many physicists believe gives time its direction, the thermodynamic arrow of time. This leads to a fascinating, though highly speculative, question. What would happen to entropy in a big crunch? The premise of the crunch is a reversal of expansion into contraction. Some physicists have theorized that if the cosmological arrow of time reverses, the thermodynamic arrow might also reverse. As the universe contracts and becomes more ordered and dense, entropy might begin to decrease. This is a difficult concept to grasp. It would imply that processes we consider irreversible would happen in reverse. Smoke might flow back into fires. Melted ice might spontaneously refreeze. In this view, the universe would not be collapsing into chaos, but into a state of perfect order, mirroring the low-entropy state of the Big Bang. If the arrow of time is defined by entropy, and entropy reverses, it raises the possibility that time itself could run backward during the contracting phase of the universe. Life in reverse. The implications. If time were to run backward in a collapsing universe, what would that be like? It is a thought experiment that challenges our intuitions about reality. From an external viewpoint, one would observe the universe rewinding. Stars would appear to unexplode, gathering gas and dust. Galaxies would unmerge and fly apart. However, for any conscious observers living within that time-reversed universe, their experience of time would likely feel entirely normal. Their arrow of time would be defined by the processes happening around them. For them, entropy would still be increasing, just in the opposite direction from our perspective. They would remember their past, our future, and be uncertain about their future, our past. Cause and effect would still seem to function for them. A glass would shatter, radiating disorder, just as it does for us. They would simply define forward in time as the direction leading toward the Big Bang, while we define it as the direction leading away from it. This idea touches upon a deep symmetry that may exist in reality, known as CPT symmetry. It suggests that the laws of physics remain the same if you simultaneously reverse time, T, swap matter with antimatter, C, for charge, and flip everything in a mirror, P, for parity. Some physicists have proposed that the Big Bang may have created our universe and a mirror universe where time flows backward from that same origin point. In this view, the Big Bang was not a beginning, but a midpoint. The philosophical implications are considerable, suggesting a block universe model where past, present, and future all exist simultaneously. Whether our universe is destined for such a symmetric fate remains unknown, but the possibility forces us to consider that our experience of time might be an emergent property of our expanding cosmos, not a fundamental truth. The cosmic rebound. A universe reborn? The concept of a singularity, a point of infinite density, represents a limit to our current theories. To resolve this, some physicists look to quantum mechanics, leading to an alternative to a final end, the Big Bounce. This idea originates from a field called loop quantum gravity, which seeks to unify general relativity with quantum mechanics. According to this theory, spacetime is not continuous but is composed of discrete quantum units. This implies there is a minimum possible size, a point beyond which space cannot be compressed. In a Big Bounce scenario, as the universe collapses, it would not reach an infinitely dense singularity. As it approached that point, quantum effects would resist further compression. Instead of collapsing completely, the universe would bounce. The energy of the collapse would trigger a new expansion, a new Big Bang. This suggests a cyclic universe, reborn from its own end, potentially for eternity. Each cycle could be similar to the last, or the laws of physics could be reset with each bounce. This model resolves the singularity problem and removes the need for a beginning of time. While Henry Tye, the physicist whose model suggests a new Big Crunch timeline, is cautious about speculating on what happens at the final moment, he acknowledges that a Big Bounce is a possibility that quantum effects might permit. However, he notes that even if a bounce occurred, the resulting universe would likely be very different from our own. The Big Bounce, much like the idea of time reversal, remains speculative. It relies on a theory of quantum gravity that has not yet been fully developed. But it serves as a reminder that the end of our universe may not be a final end, but a transition. We have journeyed from the universe's origin to its potential end, exploring a story that is far from settled. For years, the accepted narrative was the Big Freeze, a universe expanding into cold, empty darkness. As we've seen, new, high-precision data from projects like DAY and DAISY has challenged this view. There are now indications that dark energy may be weakening, potentially allowing gravity to regain control. This has revived the idea of the Big Crunch, a future where the universe reverses course and collapses. This outcome opens the door to other possibilities. Could the symmetry of such a collapse cause the arrow of time to reverse? Or could quantum forces cause the universe to bounce and be reborn? We are at a fascinating point in the history of science, where the question of our cosmic fate is once again open. Here, we predict the end of our universe, But precisely how it ends remains an open question, Henry Tai admits. The theories depend on the current data, and future observations will be the final arbiter. Upcoming projects like the Euclid Telescope and the Vera C. Rubin Observatory will map the universe with even greater precision, and they could either confirm this new timeline or lead to further revisions. For now, we are left to wonder. The universe's story is still being written, and its final chapter may be stranger than we can imagine. It is a humbling thought that during our brief existence, on a small planet orbiting an average star, we have the ability to ask these questions and begin to assemble the answers. Phantom energy, the cosmic force that will destroy reality. There is something quiet and deeply strange happening to our universe. It is a silent, invisible process, unfolding on a scale so large it is difficult to hold in the mind. For a long time, we thought we understood the grand story of the cosmos. It began with a bang, it expanded, and it was held in a delicate dance between flying apart and collapsing back in on itself. But that understanding was incomplete. In the late 1990s, astronomers looked toward the fading light of distant, dying stars and uncovered a quiet secret. The universe is not just expanding, its expansion is speeding up. Something is gently pushing everything apart, faster and faster, slowly overcoming the patient pull of gravity. It is as if a foot was pressed on an accelerator, softly at first, but with a steady, gathering pressure. This discovery opened a new chapter in our understanding of reality. We gave the cause a simple name: dark energy. It was a placeholder for a quiet and profound ignorance. This energy makes up around 68 to 70% of everything that exists, a vast, invisible ocean in which our islands of matter are adrift. For a while, the leading idea was that this energy was a constant, a simple property of spacetime itself. In that story, the universe would expand forever, growing cold, dark, and lonely. An ending some have called the heat death. But what if the story is different? What if the force pushing the universe apart isn't constant? What if it's getting stronger? There is a hypothetical form of this energy, an idea that exists at the very edge of our understanding. It's a ghost in the machine of reality, a force whose existence seems to border on the impossible. If it is real, it will not just cause the end of the universe, it will gently, but completely, unmake every particle in existence, including the ones that make you. This is not a slow fading into the night. It is a final, quiet, and universal dissolution. Cosmologists have given this idea a fittingly stark name: phantom energy. And the event it would cause is called the Big Rip, a universe in flight. To understand the phantom, we first have to understand the mystery it tries to explain. Our story begins not with a bang, but with a flicker. Imagine pointing a telescope at a deep, dark patch of the night sky, looking for a very specific kind of stellar explosion, a type Ia supernova. These are not just any dying stars, they are like cosmic lighthouses. Because of the way they happen, they all shine with almost the exact same true brightness. Think of it like seeing a field of identical light bulbs stretching off into the distance. Because you know how bright each one truly is, you can measure how dim it appears and calculate how far away it is. In the 1990s, two different teams of astronomers were doing just this. Their goal was to measure the history of the universe's expansion. The logic seemed simple and correct. The universe is full of matter, and matter has gravity. Gravity pulls things together. So, while the universe is expanding from the Big Bang, the gravity between all the galaxies should be acting like a gentle brake, slowing that expansion down over time. The only real question was whether it would slow enough to stop and reverse in a big crunch, or if it would simply slow down forever, coasting outward into the quiet. What they found felt, at first, impossible. The most distant supernovae, the lighthouses from the far edges of cosmic history, were dimmer than they should have been. There was only one quiet explanation: they were farther away than our models said they should be. And the only way for them to be farther away was if the expansion of the universe hadn't been slowing down at all. For the last several billion years, it had been speeding up. This was a discovery that quietly shifted the foundations of physics. It was like tossing a ball into the air and watching it accelerate upward into the sky, ignoring gravity. The implications were profound. Some unknown, unseen energy was at work, creating a kind of gentle, repulsive force, pushing the fabric of spacetime itself apart. This unseen force was named dark energy. The simplest explanation, one that Einstein himself had considered decades earlier, was the cosmological constant. In this view, dark energy is a fundamental, unchanging property of space. Every small piece of empty space contains a tiny, fixed amount of this energy. As the universe expands and more space is created, more of this energy comes into being, driving the expansion to accelerate at a steady, constant rate. For years, this has been the cornerstone of our standard model of cosmology. It paints a picture of a future where distant galaxies are pushed away so fast their light can no longer reach us. They will vanish from our sky, leaving our own Milky Way as a lonely island in an endless, expanding void. The universe would become a cold, dark place, but the structures within it, our galaxy, our solar system, our planet, would remain. This is the big freeze or heat death. A lonely end, but a peaceful one. But buried in the margins of our data, in the subtle uncertainties of our most sensitive measurements, lies the hint of something different. The data is consistent with a cosmological constant, but it doesn't rule out other possibilities. And one of those possibilities changes the fate of the universe from a quiet fading to a slow, but total, disintegration. A different kind of end. The entire fate of reality seems to hinge on a single number. It is a value cosmologists call the equation of state parameter, represented by the letter W. The name sounds complex, but it represents a simple ratio: the pressure the dark energy exerts divided by its energy density. This one number holds the key. For normal matter, like the atoms in your body, W is close to zero. For the simple, unchanging cosmological constant, W is exactly -1. This value represents a perfect balance, where the dark energy's density stays the same as the universe expands. But what if W is not exactly -1? What if it's just a tiny bit more negative? What if it's -1.1? At first, this seems like a small difference. But in the language of cosmology, crossing the line from -1 to anything smaller represents a fundamental shift in the nature of reality. This is the mathematical signature of phantom energy. Phantom energy is a hypothetical form of dark energy where W is less than -1. And this single property makes it unlike anything else we can imagine. For all known forms of energy, as the universe expands, their density goes down. If you have a box of matter and you double the size of the box, the density inside is cut. This feels intuitive. Phantom energy works differently. For phantom energy, as the universe expands, its energy density increases. Think about that for a moment. As space gets bigger, the concentration of this repulsive energy within it grows. More space means more phantom energy, which in turn means faster expansion, which creates more space, which generates even more phantom energy. It is a quiet, runaway feedback loop. The acceleration itself begins to accelerate. This property is so unusual that many physicists believe it must be impossible. It seems to violate fundamental ideas about energy. It suggests a substance with negative kinetic energy, a concept so strange it hints that our understanding of physics may be incomplete. It is a ghost in the equations, a phenomenon that perhaps shouldn't exist. And yet, for a time, we could not rule it out. Our measurements showed that the value of W is very close to -1. But intriguingly, some past data seemed to hint at a value slightly below -1. They were just whispers in the cosmic static, but they were persistent. More recent work, from projects like the Dark Energy Spectroscopic Instrument, tells a still more complex story. The newest evidence suggests that W may not be constant at all. It might be evolving, perhaps having been more negative in the past and becoming less so today. This makes a classic Big Rip less likely, but deepens the mystery. Dark energy might be even stranger than we thought. On one side of a line lies the cosmological constant, a universe that ends in cold, quiet isolation. On the other side is the phantom, a universe destined for a different kind of end. Because if W is, or ever was, even a fraction less than -1, it means the repulsive force of dark energy will not just push distant galaxies away. It will eventually grow strong enough to overcome every force that holds the universe together. This is the engine of the Big Rip. The mechanics of a rip. How does a force unmake reality itself? The secret lies in a quiet contest between the four fundamental forces of nature and this ever-growing phantom energy. Our universe is built on four forces. 1. Gravity. The weakest, but with the longest reach, clumping matter into planets, stars, and galaxies. 2. Electromagnetism. The force that binds atoms and molecules, holding your body together. 3. The weak nuclear force. A crucial process inside stars. 4. The strong nuclear force. The most powerful force, binding the heart of the atom itself. For 13.8 billion years, these forces have been the architects of the cosmos. A universe with a simple cosmological constant respects them. The expansion happens in the vast empty spaces between gravitationally bound things. It is too gentle to ever overcome the gravity holding a galaxy together, or the forces holding a planet together. Phantom energy does not follow these rules. Because its density increases as space expands, the repulsive force it exerts grows over time. The expansion is happening everywhere, including inside galaxies, inside solar systems, inside you. Right now, this effect is so small that the other forces overwhelm it completely. But in a Big Rip scenario, the repulsive energy in that space grows. The push becomes stronger. Imagine two people holding a rubber band. At first, they stand close, and the band is loose. This is a galaxy, held by gravity. Now, imagine the floor they stand on begins to stretch, slowly pulling them apart. For a while, their strength is more than enough to hold on. But the floor stretches faster and faster. The force pulling them apart grows. Eventually, a point is reached where their strength is not enough. The rubber band comes apart. This is what phantom energy would do to the universe. It doesn't just expand the space between galaxies. It expands the space within them, until the expansion is stronger than the gravity holding them together. Then it expands the space within solar systems, then planets, then people. Finally, it would expand the space inside the atomic nucleus itself, until its repulsive force overcomes even the strong nuclear force. The progression is a quiet, step-by-step dismantling of existence. It is not an explosion in the usual sense. It is an explosion of everything, from everywhere. Every point in space becomes a source of infinite repulsion, pushing its neighbors away. It is a true singularity, not of density like the Big Bang, but of dissolution. A rip singularity, where all matter is taken apart. A timeline for the end. If the Big Rip were our destiny, it would not be an immediate event. To understand what this would mean, let's walk through the final act of such a universe, based on a hypothetical model first worked out in 2003, which imagined a world where W was -1.5. The timing depends on that number, but the sequence of unmaking remains the same. 200 million years before the rip, the first signs would appear on the largest scales. For billions of years, gravity has pulled galaxies into clusters and superclusters. The Virgo supercluster is our own cosmic home. In this scenario, the phantom energy would grow strong enough to challenge that. The repulsive force of the expanding space within these structures would begin to exceed their gravity. Galaxy clusters would start to drift apart. The cosmic web, the very skeleton of the universe, would begin to dissolve. To an observer, the universe would seem to be growing emptier. 60 million years before the rip, the unraveling would then move to the galaxies themselves. The Milky Way is a system of hundreds of billions of stars, held together by gravity for over 12 billion years. But the phantom tide would keep rising. The repulsive force of the expanding space within the galaxy itself would overwhelm the pull of its center. Stars in the outer arms would begin to break free and drift into the void. The disk of the Milky Way would disintegrate. Our galactic island would be consumed by the ocean. 3 months before the rip, the change would then arrive closer to home. The Sun holds its planets in steady orbits. But now, the density of phantom energy would be immense. The expansion of space between the Sun and its planets would exert a force stronger than the Sun's gravity. One by one, the planets would become unbound. Jupiter would be the first to go, then Saturn. Earth would be torn from its orbit, cast away from the Sun. Our solar system would dissolve into a collection of lonely, wandering worlds. 30 minutes before the rip, the force would now be unimaginably powerful. It has overcome gravity. Now it would come for the electromagnetic forces that hold objects together. In the last half hour, the phantom energy density would become so great that the repulsive expansion of the space inside the Earth itself would overcome the forces holding the planet together. The planet could no longer hold its shape. It would simply come apart. Not from an impact, but from within. At the same time, the Sun, and every other star and planet, would be torn apart into a cloud of atoms. The final fraction of a second. The universe would now be just a uniform sea of atoms. But the process would not be finished. In the last 100 zeptoseconds, the repulsive force would grow strong enough to overcome the final pillar, the strong nuclear force. The force holding atoms together would be broken. Protons and neutrons would be ripped asunder. The very concept of matter would cease to have meaning. In the final moment, as the expansion rate approached infinity, the fabric of spacetime itself would tear. Every point would become infinitely distant from every other. The story of the cosmos would not end with a whimper. It would end in a final, quiet, and total disintegration. This journey to the edge of our understanding is built on questions. The nature of dark energy and the ultimate fate of the universe are among the greatest mysteries in science. It's a field that is always changing, with new discoveries from projects like the Dark Energy Spectroscopic Instrument and telescopes like Euclid and the Nancy Grace Roman Space Telescope. These efforts are our only way of asking these quiet, ultimate questions. If exploring these profound cosmic mysteries, from the birth of the universe to its possible endings, is something that fascinates you, consider subscribing. We dive into these topics, trying to make sense of our place in this vast and bewildering cosmos. And if you have thoughts on this, or another cosmic ending you find compelling, please share them in the comments below. The conversation about our ultimate destiny is one we should all be a part of. The lingering question. And so, we are left looking into the quiet. The Big Rip remains a hypothetical, yet plausible, fate for our universe. It is a possibility that once lurked in the error bars of our data, a phantom in the machine. Current evidence makes this specific ending seem less likely, pointing instead to a more complex, perhaps evolving form of dark energy that we are only just beginning to map. We may never know for certain. The best we may do is constrain the possibilities, pushing the most extreme fates so far into the future they become practically meaningless. But the possibility remains a quiet reminder of the universe's sheer scale and indifference. We see a cosmos filled with structure, with laws that allow for galaxies, stars, and conscious beings able to wonder about it all. We see a story of increasing complexity, unfolding over billions of years. Yet, the idea of phantom energy suggests that this entire cosmic project might be temporary. It suggests that the fundamental nature of our reality could be self-unmaking. If the universe were truly destined to tear itself apart, to erase every galaxy, every star, every atom, what would that say about our existence? Is the universe a fleeting, beautiful accident, a temporary structure doomed to an inevitable, quiet collapse? Or is the phantom just a ghost in our equations, a misunderstanding of a deeper, more stable truth we have yet to uncover? The search for that answer continues. And it is, perhaps, the most important story of all. The bubble of nothing that will erase reality. We look out at the cosmos and tend to see permanence. We see stars that have burned for billions of years and galaxies that seem to move through a kind of eternal, gravitational dance. It feels like a cosmic clockwork that has been ticking, reliably, since the beginning. But what if all of this, the stars, the galaxies, the very laws that hold them together, is a temporary arrangement? What if the foundation of our reality is a fragile state, like a china plate balanced carefully on its edge, waiting for a gentle nudge to fall? Somewhere, in the quiet, cold emptiness of space, a process may have already begun that, once started, is absolute and unstoppable. It's an idea born from the deepest questions of particle physics, and it has a name: vacuum decay. It describes the possibility that our universe is not truly stable, but is instead living on borrowed time. This isn't an idea about a distant ending, billions of years from now. It's a scenario where, at any moment, a bubble of what could only be described as a truer, deeper form of nothing could appear. A bubble that expands in every direction at the speed of light, rewriting everything it touches. Not with fire, not with an explosion, but with a silent, instantaneous change in the laws of physics. This is the story of that bubble. And perhaps the most unsettling part is that, because it moves at the speed of light, we would never see it coming. To understand this quiet, cosmic possibility, we don't need to look to the stars, but to the nature of empty space itself. The cosmic foundation, the illusion of emptiness. To begin this journey, it helps to look again at a word we think we know: nothing. When we imagine the vacuum of space, we picture a perfect void. Cold, dark, and empty. But in the language of quantum field theory, what we call nothing is one of the most complex things in the universe. The vacuum of space is not truly empty. Instead, it is a quiet, energetic sea of invisible forces known as quantum fields. It helps to think of them as invisible oceans that exist at every single point in the cosmos. These fields are the fundamental bedrock of reality. There is an electromagnetic field. When it is excited in a certain way, a particle of light, a photon, appears. There is an electron field. A vibration in that field gives us an electron. Every particle and every force that makes up you, the world around you, and the most distant star, is just a ripple in one of these underlying fields. When these fields are calm, when they are at their lowest possible energy, we call that the vacuum state. But how do we know if the state we are in is truly the lowest possible energy state? This is where a simple analogy becomes important: the image of a ball in a hilly landscape. Every system in nature wants to settle into its lowest energy state. A ball will naturally roll downhill, looking for the lowest point it can find. Once it settles at the bottom of the deepest valley in the entire landscape, it has reached what physicists call a true vacuum. It is stable. It cannot go any lower. But what if our ball didn't find the deepest valley? What if it rolled into a smaller, shallower dip on the side of a much larger hill? From the ball's perspective, it would feel stable. If you nudge it, it just rolls back to the bottom of its little dip. It has found a local minimum of energy, but not the deepest one. This is known as a false vacuum. It's a state of metastable equilibrium. It's stable for now. It's like a log of wood. It holds a tremendous amount of potential energy, but it can sit on a floor for years, perfectly stable. And yet, we know that with the right trigger, a single spark, it can release that energy and transition to a much lower, more stable state. A pile of ash. The quiet proposition of vacuum decay is that our entire universe might be in a false vacuum state. It seems stable, and the laws of physics appear constant, but there could be a deeper, more stable valley. A true vacuum that it could one day fall into. The energy difference between our reality and that potential true vacuum is a form of cosmic potential energy, waiting for a trigger. And if that trigger comes, the transition would not be gentle. It would be an instantaneous, universe-altering event. To understand what that ball on the hill actually represents, we need to talk about the field that seems to govern the fabric of existence itself, the Higgs field. The architect of our reality, the Higgs field. The ball, in our analogy, the thing whose energy level determines the state of our vacuum, is one of the most profound discoveries of modern science, the Higgs field. Unlike other quantum fields that are usually at zero in empty space, the Higgs field has a non-zero value everywhere. It's like a cosmic molasses, an invisible energy field that permeates all of space, and its existence is the reason our universe has the structure it does. For a long time, the standard model of particle physics, our best description of the fundamental particles and forces, had a quiet puzzle at its center. The equations worked beautifully for massless particles, but they struggled to explain why particles like electrons and quarks have mass. Without mass, electrons would fly at the speed of light, unable to settle into orbits around atoms. Atoms couldn't form, chemistry would be impossible, stars, planets, and people would not exist. In 1964, several physicists, including Peter Higgs, proposed a solution. They theorized an invisible energy field that filled the entire universe. As particles travel through it, they interact with it, and this interaction is what we perceive as mass. Particles that interact strongly with the field have a lot of mass. Those that interact weakly have very little. And particles like the photon, which do not interact with it at all, remain massless. For nearly 50 years, this was just an elegant theory. But then, on July 4, 2012, scientists at the Large Hadron Collider announced they had found a new particle, the Higgs boson. The Higgs boson is a ripple in the Higgs field. Finding it was direct evidence that the field itself is real. It was a monumental achievement. But with this confirmation came a quiet, unsettling thought. The properties of the Higgs boson, specifically its mass, gave us a way to measure the character of the Higgs field itself. Its mass is about 125 giga-electronvolts, GeV. When physicists put this value, along with the mass of another particle called the top quark, into the equations, they found a strange result. The numbers suggested that the energy level of our Higgs field, the vacuum we live in, might not be at the lowest possible point. The specific mass of the Higgs seems to place our universe on a razor's edge, in a state described as metastable. It's not perfectly stable, but it's not wildly unstable either. It seems to be in a false vacuum. Our universe exists in that shallow dip on the side of the cosmic hill. Stable for now, but with the potential for a fall. This isn't just a guess, it comes from running the equations of the Standard Model up to incredibly high energies. The calculations show that if the Higgs field were agitated with enough energy, it might not just return to its current state. It could be pushed over the energy barrier and tumbled down into a new, lower energy state, the true vacuum. This discovery transformed the Higgs boson from simply the giver of mass into a potential indicator of our cosmic fragility. It provides a physical mechanism for how our reality could be temporary. The next question, of course, is what could possibly give it that push? The answer lies in one of the quietest and strangest rules of quantum mechanics. The quantum glitch, how to start the end. In our analogy of the ball in a shallow dip, how does it get to the deeper valley below? In the world we experience every day, there's only one way. You have to give the ball enough of a kick to push it up and over the rim of the dip. This energy barrier is what keeps our false vacuum stable, and the energy required to kick a piece of the Higgs field over it is immense, far beyond anything we can create. If this were the only way, our universe would be safe. But the universe, at its smallest scales, plays by a different set of rules. It plays by the strange, probabilistic rules of quantum mechanics. And in the quantum world, you don't always have to go over the hill. You can go straight through it. This is called quantum tunneling, and it is a confirmed part of how our universe works. It's so strange it sounds like something imagined rather than real. Imagine throwing a tennis ball against a solid wall. You would expect it to bounce back every time. But in the quantum realm, there is a tiny, but real, probability that on one of those throws, the ball will simply appear on the other side of the wall, without ever having broken it. This happens because quantum objects, like particles and fields, also behave as waves of probability. The wave that describes a particle isn't entirely contained on one side of a barrier. A faint part of that wave can extend through the barrier to the other side. And if that happens, there's a chance the particle will just appear there. There is something quietly humbling about this. It isn't just a theory, quantum tunneling is the reason our sun shines. The pressure at the core of the sun is not high enough to force hydrogen nuclei to fuse together classically. They do it by quantum tunneling through the energy barrier that separates them. This same quiet glitch is the most likely trigger for the end of our universe. Somewhere, in the vastness of space, a tiny patch of the Higgs field doesn't need to be kicked over the energy hill. Through a purely random, spontaneous quantum fluctuation, it can simply tunnel through the barrier. In that one tiny point in space, the Higgs field instantly snaps from its false vacuum value to its true vacuum value. A tiny speck of the universe falls into the deeper valley. And in that instant, a bubble is born. A bubble of true vacuum. This event could happen anywhere, at any time. It doesn't need a cause. It can be a purely random event, a fundamental probability built into the fabric of a metastable universe. And once that bubble forms and grows beyond a certain small size, its fate, and ours, is sealed. The cataclysm, birth and expansion of the bubble. The moment a region of the Higgs field tunnels to its true vacuum state, a bubble of a new reality is born. This bubble isn't empty space, it is space with a lower energy. The difference in energy between the false vacuum outside the bubble and the true vacuum inside is enormous, and this energy fuels the bubble's expansion. The boundary of the bubble, its wall, has a kind of surface tension. At first, this tension tries to make the bubble collapse. But if the bubble is born large enough, the outward pressure wins. The energy released by the vacuum-changing state is converted into the energy of the bubble wall, causing it to expand outwards at a speed that almost instantly reaches the speed of light. What happens inside this bubble is a fundamental rewriting of the properties of space. Inside the bubble, the Higgs field has a new, lower value. This means the way it interacts with all other particles changes. The masses of fundamental particles like electrons and quarks would instantly be altered, or they might disappear altogether. The delicate balance of the universe's fundamental forces would be broken. The laws of chemistry depend on the precise mass of the electron and the properties of electromagnetism. If those change, stable atoms as we know them could no longer exist. Atomic nuclei could fly apart. It is not an explosion in the way we usually think of one. An explosion is a release of energy into the space around it. This is a transformation of space itself. There would be no sound, no flash of light to announce its arrival. It would be a silent wave of physical law change, unmaking existence as it passes. Imagine this wave sweeping through a galaxy. As the bubble wall arrives, a star and its planets simply cease to be what they were. The matter they are made of is converted into some new form of matter and energy, consistent with the new, alien laws of physics inside the bubble. From the outside, you would see nothing until the moment the bubble wall reached you. The space the galaxy once occupied would now be part of the expanding bubble, a region of the universe with a completely different operating system, one that is hostile to any structure we can conceive of. This process is unstoppable. Once started, the bubble of true vacuum is the most stable thing in the universe. It will continue to expand at the speed of light until it has converted every part of our false vacuum universe into the true vacuum. It is the universe's final, irreversible phase transition. And its most unsettling property is not just its power, but its profound stealth. The ultimate blind spot. Why we'd never see it coming. Here lies the quiet, deep strangeness of vacuum decay. It's not just that it would unmake everything, it's that we would have no warning at all. The destruction and the news of the destruction arrive at the exact same moment. The reason is simple and absolute. The bubble wall expands at the speed of light. And according to Einstein's theory of relativity, the speed of light is the ultimate cosmic speed limit. No information can travel faster. Imagine a vacuum decay event happens in the Andromeda galaxy, about 2.5 million light-years away. The moment the bubble begins to expand, the very first particles of light from the event also begin their journey toward us. But the bubble wall is traveling at the exact same speed as those photons. They are in a perfect race, and it is a race the photons cannot win. From our perspective on Earth, our telescopes would continue to see the Andromeda galaxy as it was, completely normal. For 2.5 million years, as the bubble silently expands across the void, we would remain in blissful ignorance, unaware that a wave of oblivion was on its way. Then, one day, the bubble wall would arrive. But we wouldn't see a bubble appearing in the sky. The moment the leading edge of that bubble reached Earth, it would simultaneously reach our eyes, our telescopes, and every atom in our bodies. There would be no time to process, no time to fear. One instant, you are here. The next, you, the Earth, and the very concept of you are gone, rewritten by the new physics of the true vacuum. It is the perfect, undetectable cosmic event. It might have already happened. A bubble could have formed a billion years ago in a galaxy a billion light-years from here. Right now, a sphere of cosmic change could be expanding through the universe, having already rewritten millions of galaxies. We would have no way of knowing. Every star we see is a confirmation that the bubble has not yet reached it on its path to us. But it tells us nothing about a bubble that might have started somewhere else. This single fact elevates the idea of vacuum decay from a distant, abstract possibility to something more immediate. It is a threat that is, by its nature, completely invisible until the moment of impact. This forces us to ask a quiet, unsettling question. How likely is it? And should we be worried? The evidence and the odds, should we panic? So, is it time to worry? The short, and thankfully reassuring, answer is almost certainly no. While the theory of vacuum decay is built on solid physics, the actual probability of it happening is thought to be incredibly small. The reason for this comes back to our analogy of the ball on the hill. The stability of our false vacuum depends on the height and width of the energy barrier. Current calculations, based on the mass of the Higgs boson and the top quark, suggest that while we are in a metastable state, the hill is likely very, very high and very, very wide. This means the probability of a spontaneous tunneling event happening is fantastically low. Physicists have tried to estimate the lifetime of our universe. The numbers are so large they are hard to comprehend. One estimate suggests it would take longer than 10 to the power of 100 years for a bubble to form. The current age of the universe is only about 13.8 billion years, a tiny fraction of that time. So, spontaneous decay is probably not something we need to lose sleep over. There's also a powerful piece of evidence that suggests our universe is quite stable. We are still here. The early universe was an incredibly hot and energetic place. If our vacuum were highly unstable, The extreme conditions right after the Big Bang should have been enough to trigger a decay event almost immediately. The fact that the universe survived that time and has existed for 13.8 billion years suggests the energy barrier is indeed immense, or perhaps there is something missing from our equations. It's entirely possible that the standard model of particle physics is incomplete. Many physicists believe there are new particles and forces we haven't discovered yet. It could be that one of these yet-to-be-discovered particles interacts with the Higgs field in a way that makes our vacuum completely stable after all. In this case, our universe would be in a true vacuum, and this entire discussion is a portrait of a possibility that doesn't apply to us. Scientists are actively working to test these ideas. Recent experiments, like those in 2024, have even managed to create and observe a process similar to vacuum decay in controlled lab settings using supercooled atoms. By creating a false vacuum in these atomic systems, they could watch bubbles of a true vacuum form and expand. These experiments confirm that the mathematics of the theory are sound, even if the odds of it happening to our universe are tiny. So, while the idea is real in theory, in practice, it is one of the most remote of all possible cosmic endings. If this kind of calm exploration into the nature of things helps you unwind, consider subscribing to the channel. Your curiosity helps us continue to explore these quiet, deep questions. And wherever you are right now, feel free to share where you're watching or listening from. The conclusion: the beauty of a fragile cosmos. So, we've journeyed to the edge of reality and thought about our own instantaneous transformation. And after all that, we've come to the reassuring conclusion that we are, almost certainly, safe. Why, then, do physicists spend time thinking about such a possibility? The answer is that vacuum decay is not really a doomsday prediction. It is a powerful diagnostic tool. By pushing our best theory of physics to its absolute limits, we can find the places where it might be incomplete. The question of the vacuum's stability isn't about predicting the end, it's about understanding the beginning. If our calculations show the universe should be unstable, but we see that it is stable, it gives us a signpost pointing toward new physics and a deeper understanding of reality. There is also something quietly humbling about the idea. We tend to view the laws of physics as absolute. But this concept reminds us that what we observe might only be the local rules of our particular cosmic neighborhood. In another state, with different physical laws, existence could be structured in a way we can't begin to imagine. Our universe, with its perfect tuning for stars, chemistry, and life, might be an incredibly special and fragile exception. There is a strange beauty in this. The possibility, however remote, that our existence is temporary doesn't have to be a source of fear. It can be a source of wonder. It reframes the universe not as a static stage, but as a dynamic, evolving thing. It imbues our existence with a sense of preciousness. We are living in a remarkable, perhaps temporary, bubble of stability that has allowed for incredible complexity to arise. Knowing that the foundation of reality could be fragile doesn't diminish it, it enhances it. It makes the light from a distant star, the intricate dance of a living cell, and our own fleeting consciousness all the more extraordinary. We are the universe's way of observing itself, for a time, from within this quiet, metastable dip on a vast cosmic hillside. The knowledge that a deeper valley may exist shouldn't fill us with dread for the fall, but with appreciation for the view we have right now. It reminds us that the cosmos is still full of mysteries. The universe may be fragile, but the wonder it inspires is not. What the end of everything actually looks like. Imagine a future. Not a future of flying cars, but a future so profoundly deep in time that even black holes haven't survived. For decades, the story science told us was one of a heat death, a universe expanding forever until it became a cold, dark, and empty void. A state of perfect, unshakable stillness. It's an end that doesn't come with a bang, but with a slow, silent exhale that lasts for an eternity. This was the most widely accepted scenario. But what if that story, the one we've been telling ourselves for a generation, is wrong? As of 2026, startling new data has emerged that might completely rewrite the final chapter of the cosmos. The end of everything may not be a cold, quiet fade to black. It might be a violent, fiery collapse into the very point where it all began. The Great Reversal. For years, we believed the universe's expansion was not only happening, but accelerating, driven by a mysterious force called dark energy. The idea was that this force acted like a constant, cosmic anti-gravity, relentlessly pushing everything apart. But recent data from the Dark Energy Survey, DE, in Chile and the Dark Energy Spectroscopic Instrument, DESI, in Arizona suggest something astounding. These observatories, after mapping millions of galaxies, have found hints that dark energy may not be constant at all. In fact, it might be weakening. Some models based on this new data point to a shocking conclusion. The cosmological constant could be negative. If this holds true, it means that the anti-gravity pushing the universe apart will eventually fade, and gravity, the patient, pulling force of all the matter in the cosmos, will take over. The expansion would slow down, stop, and then reverse. According to calculations based on this 2026 data, the universe could reach its maximum size in about 11 billion years, and then begin the long fall back inward, culminating in a big crunch, roughly 20 to 33 billion years from now. Instead of expanding forever, the universe would be like a stretched rubber band, snapping back to where it started. The sky catches fire. So, what would this great collapse actually look like? At first, the changes would be subtle. For a few billion years after the universe reaches its maximum size, things might not seem all that different. But an astronomer on a far future Earth would notice something remarkable happening in the sky. For our entire history, we've observed that distant galaxies are moving away from us. Their light, redshifted, to longer, redder wavelengths. In a collapsing universe, we would see the opposite. Galaxies would stop receding and begin rushing toward us. Their light would become blue shifted, shifting to higher energy, bluer wavelengths. The night sky, once a portrait of departure, would become a scene of cosmic convergence. As the collapse accelerates over billions of years, the universe gets smaller, hotter, and more crowded. The space between galaxies vanishes as they begin to merge. But the most dramatic change would come from the sky itself. The cosmic microwave background, CMB, the faint, cold afterglow of the Big Bang, would be compressed along with everything else. As it gets compressed, its temperature would soar. The sky would begin to glow, first a dull red, then a brilliant orange, and eventually a searing, white-hot blaze. The background radiation of the universe would become hotter than the surface of stars, cooking planets and vaporizing any structure that hadn't already been destroyed by galactic collisions. The Big Crunch. In the final moments, the universe would be an unrecognizable inferno. It wouldn't be a graveyard of cold relics, but a crucible of unimaginable energy. Stars, no longer isolated points of light, would merge and collide in a gigantic cosmic pile-up. The universe would become so dense and hot that not even atoms could survive. Everything would dissolve into a plasma of fundamental particles, crushed together as spacetime itself closes in. In the last fraction of a second, all the matter and energy of the cosmos would fall into a single point of infinite density and temperature, a singularity. The Big Crunch is, in many ways, the Big Bang in reverse. It isn't a slow, peaceful end. It's a breathtakingly violent conclusion where the universe, born from a single point, returns to one. It's not an exhale, it's a final, all-consuming inhale. The ghost of a different future. So what about that other story? The one about the cold, dark, endless future? For a long time, the heat death was our best guess, and it's a mind-bending journey in its own right. That narrative assumed dark energy was a constant push, and it would have unfolded over timescales that dwarf the Big Crunch scenario. In that alternate future, the age of stars, our Stelliferous Era, would end when the last, most frugal red dwarf stars finally flicker and die, perhaps after 10 trillion years. The universe would then enter the Degenerate Era, a cosmic graveyard populated by stellar corpses like white dwarfs and neutron stars. Here, the most patient process of all would take over: proton decay. Grand unified theories predict that protons, the building blocks of matter, aren't truly stable, but may decay over immense timescales, with a half-life of at least 10 to the power of 34 years. Over countless eons, every star, planet, and object would slowly evaporate into a mist of radiation. This would lead to the black hole era. After 10 to the power of 40 years or so, only black holes would remain. But even they weren't forever. Thanks to Stephen Hawking, we know that black holes slowly evaporate through Hawking radiation. A solar mass black hole would take around 10 to the power of 67 years to vanish, while the largest supermassive black holes could last for a Google 10 to the power of 100 years. Finally, after the last black hole evaporated, the universe would enter the dark era, a vast, cold, and impossibly empty void, where time itself would lose meaning. Some highly speculative ideas even suggested a new universe could be born from a random quantum fluctuation, a Poincare recurrence, or a sudden change in the nature of the vacuum, false vacuum decay. These are incredible concepts, but if the latest evidence for a big crunch is correct, the universe won't have the time to go through any of it. We began with a question: what does the end of everything actually look like? For a long time, the answer was a cold, lonely fade into nothingness. A universe at peace, but a peace born of emptiness and exhaustion. But science is a story that is constantly being revised. The latest evidence from 2026 suggests a far more dramatic and perhaps more poetic ending. Instead of a big freeze, we may be heading for a big crunch. The end may not be a cold, empty void, but a fiery return to the beginning. This new picture transforms the ultimate fate of the universe from a quiet slide into oblivion into a violent, cyclical reunion. All the matter and energy that burst forth in the Big Bang would be brought back together in a final, spectacular collapse. It's an ending that doesn't just close the book on our universe but slams it shut, perhaps setting the stage for the next Big Bang to follow. The cosmos, it seems, might not just become silence, it might be destined to return to the sound and fury from which it was born.